They're three of the biggest names on the road, and behind each one is a factory operation running at incredible speed and scale. From Toyota's lean production lines to Honda's robotic precision and Ford's powerhouse assembly systems, these vehicles are built with decades of innovation baked into every step. In this video, we're going inside the factories to reveal how Toyota, Honda, and Ford turn raw materials into machines trusted around the world. To understand how a Toyota car is made, one must first step into a space where discipline, precision, and respect for process define every movement, the Toyota factory. Within these facilities, the transformation from raw materials to a fully functional vehicle is not simply a mechanical progression, but a living manifestation of a philosophy. This philosophy, known globally as the Toyota Production System, or TPS, is centered on two foundational pillars: Jidoka, automation with a human touch, and just-in-time manufacturing. Together, these principles dictate how every Toyota vehicle is born. Imagine walking into one of Toyota's flagship plants, such as the Tsutsumi plant in Toyota City, Japan, or the Georgetown facility in Kentucky. The air is filled not with chaos, but with a quiet, rhythmic hum. It is not the sound of urgency, but of synchronization. Workers, robots, and machines operate in precise harmony, each step of the process unfolding like clockwork. Every bolt tightened, every part aligned, every inspection performed. Nothing is rushed, but nothing is delayed. The objective is not to build fast, but to build flawlessly, and in the smallest increment of time and resource necessary. The beginning of any Toyota vehicle starts far upstream, not in the plant itself, but in the raw material supply chain. Toyota sources high-strength steel, aluminum, plastics, semiconductors, glass, and countless other materials through a tightly managed supplier network. Each supplier is held to stringent quality and delivery standards. Deliveries arrive at the plant just in time, often within hours of their use. This lean inventory philosophy reduces waste and ensures that the factory remains agile, able to adapt to shifting demands or changes in vehicle variants without maintaining massive backstocks. Once materials arrive, the first physical steps in vehicle creation occur in the stamping shop. Here, massive coils of steel or aluminum are loaded into enormous stamping presses, machines that weigh hundreds of tons and exert enough force to shape thick metal in a single, clean motion. These presses are fitted with die sets, precision-engineered molds that stamp out individual body components like fenders, hoods, roofs, and doors. The dies are swapped out by automated systems within minutes, allowing the line to shift seamlessly between models with minimal downtime, a critical capability in a mixed model facility. The stamped panels are then transported, often via overhead conveyor systems or autonomous carts, to the welding shop, the domain of the body in white. Here, the core structure of the car takes shape. Robotic arms, fitted with weld guns and sensors, orchestrate a ballet of sparks. These machines are programmed with exacting specifications to apply spot welds at predefined intervals, securing body panels together into a rigid, cohesive structure. Human technicians oversee the process, performing inspections, handling complex geometries, and activating andon systems, alert cords, should any defect be found. Toyota's concept of Jidoka is exemplified here. Each welding station is empowered to halt the entire line if a defect or misalignment is discovered. This is not seen as failure, but as a safeguard for quality. Rather than allow a potentially flawed product to progress, the issue is stopped at its source, analyzed, and resolved before production resumes. Workers are trained not just to follow instructions, but to improve the process. This continuous improvement culture, known as Kaizen, is deeply embedded in every team member, from entry-level assemblers to plant managers. Once the car body has been assembled and verified for dimensional accuracy using laser measuring systems, It proceeds to the paint shop, where it is cleaned, sealed, primed, and finally painted. Before any color is applied, the body is immersed in a series of baths for electrodeposition coating, a process that prevents corrosion by electrically bonding a primer to the metal surface. The body then moves through a drying oven before entering the color application booths. Inside the paint booths, robotic arms fitted with rotary atomizers apply successive layers of primer, base coat, and clear coat. Each coat is inspected under intense lighting and humidity-controlled conditions to ensure consistency and to prevent inclusions such as dust or overspray. Technicians perform visual inspections and touch tests, sometimes sanding and reapplying paint if surface imperfections are found. The body then enters a final curing oven, where it is baked at high temperatures to harden the paint finish. By now, the car's basic structure is complete and coated, but it still lacks its soul: the engine, drivetrain, electronics, and interior. These elements come together in the general assembly area, a zone that stretches across hundreds of meters and involves hundreds of interwoven processes. It is here that Toyota's just-in-time philosophy truly comes alive. Unlike traditional batch manufacturing, Toyota's production line is mixed model, meaning different car types and trims, even with different engines or drive systems, are produced on the same line in whatever sequence is dictated by real-time customer orders. To accommodate this, parts are delivered in sequence to the line. If the next car is a Corolla hybrid with a panoramic roof, the exact seat configuration, roof headliner, battery pack, and other components for that configuration arrive seconds before the car reaches the station where they'll be installed. One of the most critical events in the assembly process is known as the marriage, the point at which the painted body is lowered onto the pre-assembled chassis. The chassis includes the engine, transmission, suspension components, exhaust system, and drivetrain. These assemblies are built up in parallel lines and synchronized with the main body line so that both components arrive at the marriage station at precisely the same moment. As the body descends onto the chassis, guided by precision jigs and hydraulic lifts, technicians align mounting points and fasten critical bolts using torque-controlled tools. Every fastening operation is digitally logged and monitored. If a bolt is under or over-torqued, or if a tool slips, the system immediately alerts the operator. These digital confirmations ensure traceability and enable Toyota to maintain records for every car that leaves the factory, supporting future warranty claims, recalls, or quality assurance audits. After marriage, the car begins to take on its recognizable interior form. Dashboards are installed as single pre-assembled units, often produced by Tier 1 suppliers in nearby satellite facilities and delivered just in sequence. Seats, wiring harnesses, air conditioning modules, infotainment systems, and airbags are carefully installed in a series of tightly choreographed steps. Workers use a combination of hand tools, smart torque guns, and pick-to-light systems, which light up the exact part bins for each operation to ensure accuracy and speed. This process continues with the installation of glazing, lighting elements, bumpers, wheels, and various trim components. Every part is fitted under strict quality standards with gap alignment and surface flushness, checked visually and digitally using laser systems. During each step, workers remain empowered to pull the and-on cord if they detect an anomaly, reinforcing Toyota's belief that quality is built in, not inspected in. Once the assembly is complete, the vehicle is no longer a shell or a skeleton. It is a living machine, but one that has not yet been proven. The next phase will test every system, calibrate every sensor, and ensure that the Toyota badge on the front carries with it the weight of reliability, safety, and trust. Following the completion of physical assembly, each Toyota vehicle enters one of the most critical phases of the production lifecycle: the inspection, calibration, and functional testing stage. This is where mechanical craftsmanship meets analytical scrutiny. Every car must now prove that it not only fits together correctly, but that every system operates as designed, with the precision and reliability Toyota is globally known for. The first area the vehicle enters is typically the initial quality gate. Here, a multi-point check is performed by trained inspectors who methodically examine structural components, body alignment, and basic mechanical fitment. Every door, trunk, and hood is opened and closed to assess alignment and sound. Uneven gaps, misaligned panels, or abnormal resistance are noted and corrected on the spot. Workers use gap gauges, flushness sensors, and manual inspection tools to detect even the smallest deviations in build quality. From there, the vehicle proceeds to dynamic system checks. This is where the car begins to come to life, electronically and mechanically. A technician connects the vehicle to a factory diagnostic system, uploading the final software package to all electronic control units. In a modern Toyota, there can be 30 to 80 ECUs depending on the model, each managing a different subsystem, such as braking, power steering, stability control, hybrid drive, airbag systems, and infotainment. The ECUs are flashed with firmware specific to the car's trim level, engine type, and market destination. This step is highly sensitive, with redundant data verification systems to ensure the software uploads completely and correctly. Once configured, the system initiates a global self-check, where the vehicle essentially performs a diagnostic scan of itself. Each ECU confirms its functionality and readiness, while the technician monitors for error codes or inconsistent behavior. Any anomaly is logged and triggers a deviation procedure where the vehicle may be diverted to a separate diagnostics bay for deeper troubleshooting. Next, the car is transferred to a specialized station for fluid filling and pressure testing. Here, automated systems dispense exact volumes of engine oil, brake fluid, coolant, washer fluid, and, for hybrid or electric models, inverter coolant or battery thermal management fluids. These filling stations are digitally calibrated to prevent overfilling or contamination. During this stage, systems are also pressurized and sealed, then tested for leaks using pressure sensors and flow meters. Brake lines are tested by pressurizing the system and monitoring for pressure drops, ensuring every car leaves with a perfect, air-free hydraulic system. At this point, the vehicle is ready for its first engine start. A technician initiates ignition using either a key fob or the factory diagnostic console. The vehicle turns over and the engine comes to life. During this brief but critical startup phase, the system monitors RPM, oil pressure, exhaust sensor feedback, charging voltage, and other vitals. The technician listens for abnormal engine noise, checks idle quality, and watches for leaks or warning indicators. Once the engine stabilizes, the vehicle begins a series of automated or semi-automated functional tests, including shifting through gears, verifying steering assist, and checking basic throttle response. With the engine running and fluid circulating, the vehicle now moves to the dynamic test track or rolling road, depending on the facility's layout. On a rolling road, a stationary test bench with rotating drums. The car is accelerated through a simulated driving sequence. Braking, acceleration, shifting, emissions control, and hybrid transitions are all tested under load. This is where software calibration is fine-tuned. For example, hybrid systems may be evaluated for smooth transitions between electric and gasoline power, while adaptive cruise control sensors are calibrated to recognize distance targets. Meanwhile, headlight aim is adjusted using laser-guided alignment equipment. Wheel speed sensors are tested, and the vehicle's onboard safety systems, such as ABS and traction control, are confirmed to respond appropriately to artificial inputs. On some high-spec models, even the sound insulation is checked using internal microphones while simulating wind and road noise inside a soundproof chamber. Following dynamic testing, the car is driven to a water test booth, an enclosed chamber equipped with high-pressure nozzles, positioned to simulate heavy rain, splash conditions, and high-speed water exposure. The entire vehicle is blasted with water from above, below, and the sides. Technicians inside the booth or using moisture detection tools afterward check the interior for any signs of leakage, particularly around doors, glass seals, sunroofs, and underbody grommets. Vehicles that fail this test are sent to a specialized sealing team for inspection and repair before re-entering the final inspection queue. The penultimate step in the process is the final visual and tactile inspection line, often referred to as the white light tunnel. In this area, powerful overhead lights and side lighting replicate broad daylight, revealing surface imperfections invisible under factory lighting. Inspectors move around each vehicle slowly, checking for micro scratches, paint defects, misaligned trim, dirt under the clear coat, and material inconsistencies. The tactile elements are just as important: seat firmness, stitching alignment, trim tightness, and even the smoothness of control knob rotation are checked against factory benchmarks. Finally, once all systems are verified, paint and finish are pristine, and data records confirm the vehicle's complete build and performance history, the car is released from production. A digital certificate is issued, containing every measurement, torque value, fluid fill, software version, and test result from each phase of assembly. This data is stored in Toyota's secure manufacturing archive and is linked to the vehicle's VIN for life. If a component recall, software update, or warranty claim ever arises, this record becomes the reference point for diagnostic and corrective action. As a last step, protective films are applied to vulnerable surfaces like the hood, doors, and bumpers to prevent damage during transport. The vehicle is then driven to the shipping yard where it is scanned, parked, and queued for delivery via truck, rail, or ship, depending on its final destination. The birth of a Honda automobile is not an accidental fusion of metal, glass, rubber, and electronics. It is the physical realization of a manufacturing philosophy rooted in discipline, simplicity, and human respect. At the core of Honda's automotive production process is the concept of monozukuri, a Japanese term meaning making things with craftsmanship and pride. For Honda, monozukuri is not just about building cars. It's about building trust in every nut and bolt, in every weld seam, in every panel gap. To witness a Honda car being built is to enter a tightly orchestrated environment where technological sophistication meets manual precision. Inside one of Honda's production facilities, such as the plant in Marysville, Ohio, or the Sayama factory in Japan, the scale is staggering. These plants are sprawling ecosystems of autonomous vehicles, robotic cells, and human operators working side by side across multiple production halls. And yet, despite their size and complexity, the rhythm of the process remains surprisingly calm. Everything flows according to plan, governed by Honda's unique lean manufacturing philosophy known as the Honda Production System. The journey of a Honda car begins long before any metal is cut. It starts with production planning, a phase driven by market forecasts, dealer input, supply chain readiness, and model demand. Honda's plants operate on a build-to-order basis more than most automakers. That means production schedules are crafted based on actual customer orders and real-time market demand. This approach minimizes inventory waste and maximizes the efficiency of the supply chain. Once the schedule is locked in, suppliers across the globe begin preparing the thousands of components that will soon converge at the plant. Raw materials like steel and aluminum arrive at the factory in massive coils. These materials first enter the stamping department, a cavernous space filled with towering hydraulic presses. Each press is fed with sheet metal, and fitted with enormous dies. Complex mold tools, shaped to form specific vehicle panels, such as hoods, doors, roofs, and fenders. The dies are interchanged automatically using massive overhead cranes and quick change systems, allowing the factory to shift between different vehicle models with incredible speed. These presses apply thousands of tons of force in milliseconds, transforming flat sheet metal into high-precision components with reinforced curves and load-bearing geometries. Each stamped panel is checked using template gauges or laser measuring arms to verify its accuracy against design tolerances. Honda's emphasis on dimensional precision at this early stage ensures that all panels fit perfectly during final assembly, which in turn improves both structural integrity and noise insulation. The stamped panels next travel to the welding shop, where the vehicle's skeleton, known as the body in white, is assembled. This stage is a symphony of automation. Dozens of robotic arms arc and swivel across each cell, welding panels together with pinpoint accuracy. These arms are fitted with spot weld guns, seam welders, laser cutting tools, and even rivet actuators, all pre-programmed for the vehicle model and trim level currently on the line. Guided by 3D coordinates, these robots can perform hundreds of welds in just a few minutes. Despite this high degree of automation, human workers play a vital role. Technicians monitor robotic operations, inspect weld seams visually, and perform manual welding in areas where robots cannot easily reach, such as complex internal joints or tight cavities. Importantly, Honda applies its stop-the-line authority in this department. Any associate who detects an issue is empowered to halt the line and initiate corrective measures immediately. This is part of Honda's respect for humanity approach, trusting operators not just to follow instructions, but to contribute actively to product quality. Once the weld shop produces a complete body shell, it enters the sealing and corrosion protection area. At this stage, structural adhesives and sound dampening materials are applied to critical areas of the body, such as the floor pan, roof seams, and door frames. These materials increase rigidity, improve crash performance, and reduce road noise. Seams are also sealed with flexible gaskets to protect against water ingress. After sealing, the body is conveyed to the paint shop, one of the most technologically advanced sections of the plant. Before any color is applied, the car is submerged in a series of cleaning and surface preparation baths. These include alkaline washes, acid baths, and a crucial e-coating step, in which the entire body is dipped in an electrically charged primer solution. The electrical current causes corrosion-resistant particles in the bath to bond uniformly with the metal, even in hard-to-reach crevices and weld joints. Once the e-coat is cured in an oven, the body enters a clean room environment for the color painting process. Robotic arms with electrostatic spray guns apply the primer, base coat, and clear coat in successive layers. Each layer is air-dried or heat-cured to ensure optimal adhesion and durability. Honda's paint robots use feedback-controlled nozzles that adjust spray patterns dynamically based on body shape and angle, reducing overspray and minimizing environmental impact. Between layers, the vehicle is visually inspected under specialized lighting conditions. Technicians look for drips, dust contamination, and color uniformity. If any issues are found, the body is flagged for manual repair, which may include sanding, buffing, or repainting a specific panel. Once painting is complete and the final clear coat has cured, the body is ready for general assembly, the stage where it transforms from a painted shell into a fully functioning automobile. Before reaching the general assembly line, however, many key sub-assemblies are built in parallel feeder lines located throughout the plant. These include engine and transmission modules, suspension components, dashboards, interior trim sets, seat assemblies, and wiring harnesses. Honda practices a synchronized sub-assembly strategy. Each of these components is produced and sequenced in real time to meet the exact build order of the cars progressing down the main assembly line. That means if car number 287 is a Honda Accord hybrid in touring trim, every part of that specific configuration is queued and ready to install by the time the body reaches the relevant station. When the painted body reaches the main assembly line, it is mounted onto a moving conveyor system. This conveyor will carry the vehicle through dozens of stations, each performing a specific set of installations or tests. The first few stations focus on interior preparation. Sound deadening mats are applied to the floor. Wiring harnesses are routed through the firewall and chassis, and the dashboard is bolted into place. Honda uses pre-assembled dashboard modules, which include the instrument cluster, HVAC system, infotainment screen, and most switches, all pre-tested before installation. This reduces line complexity and improves consistency. Seats, carpeting, door panels, and airbags follow shortly after. At every step, workers use a system of digital instructions, torque control tools, and pick-to-light part bins to ensure that the right part is used and installed to the correct specification. Honda's goal is zero deviation from build order, even in mixed model lines, producing different trims every few minutes. As interior installation continues, the process becomes more intricate. With the dashboard now secured, the vehicle receives its electrical control units, sensors, and remaining interior electronics. These are connected to the pre-installed wiring harnesses using color-coded, click-locked connectors that help eliminate the possibility of human error. Specialized quality control stations may test critical modules immediately after connection, especially airbag sensors and crash detection systems, to ensure they are responsive and correctly integrated into the vehicle's network of ECUs. Following this, attention turns to glazing and weather sealing. Robots or trained technicians carefully install front and rear windshields, applying adhesive in a uniform bead to ensure a perfect seal. The installation is timed precisely as the adhesive cures rapidly. Door windows, quarter glass, and side mirrors are added next, with their mechanisms tested on the spot to ensure smooth operation. Throughout this process, jigs and fixtures are used to maintain tight tolerances between the panels and glass, ensuring aerodynamic integrity, road noise insulation, and weather protection. The vehicle then reaches one of the most pivotal points in the production process, the powertrain marriage. As the body travels down the assembly line, a pre-assembled drivetrain module consisting of the engine, transmission, front or all-wheel drive differential, and suspension subframe arrives underneath on a separate conveyor. The marriage station uses synchronized hoists and laser-guided platforms to lift the body and lower it gently onto the drivetrain assembly. Once aligned, operators bolt the body to the subframe using hydraulic torque tools, which log each torque application in real time for quality traceability. The process of mating the body to the chassis and powertrain is more than a mechanical operation. It's an integration of identity. From this moment, the car ceases to be a shell and becomes a functional vehicle. After the marriage, systems are connected. The fuel lines, brake lines, wiring looms for sensors and control modules. Axles are bolted in. Radiators and intercoolers, along with their coolant hoses, are fitted. Exhaust systems are clamped into place and routed along the underbody using guides to prevent rattle or contact with heat-sensitive zones. Next come brake systems and suspension components. Brake calipers and discs are attached at each corner, followed by routing and fastening of hydraulic lines. ABS sensors and wheel speed sensors are snapped into their mounts, and their cables are clipped securely to avoid movement. Meanwhile, shock absorbers, coil springs or struts are fastened to the body using calibrated robotic arms or torque-controlled tools operated by line workers. These fasteners are critical as they influence ride quality, safety, and steering behavior. The wheels and tires, pre-mounted and balanced in a separate line, are then delivered just in time to the vehicle. They are aligned to the hub assemblies and fastened using pneumatically powered tools equipped with digital torque sensors. Each wheel torque is logged and checked against specifications. Even minor deviations trigger alerts. For instance, over-tightening a lug nut can damage threads or warp brake rotors, so precision is not optional. By this stage, the vehicle is mechanically complete, but not yet operational. It now passes into a startup and calibration zone, where the first true interaction between systems begins. Trained technicians perform a key-on sequence where all electronic systems are activated. This step includes powering up the main vehicle bus, initializing communication between ECUs, and performing a cold test of lighting systems, instrument clusters, wipers, and cabin electronics. The technician uses a diagnostic console to verify proper communication between modules and applies any last-minute software updates if required. Once the vehicle's systems are verified and error-free, the engine is started for the first time. A moment that is both mechanical and symbolic. As the engine cranks and catches, onboard diagnostics immediately monitor oil pressure, exhaust emissions, idle speed, coolant flow, and electrical charging. If any of these parameters fall outside of the calibrated range, the system flags the vehicle for further inspection. For hybrid models, the electric drive system may initiate instead, with the gasoline engine starting only after the battery's state of charge reaches a specific threshold. After the successful start, the car enters the rolling road test or chassis dynamometer. Here, it is strapped to large rollers that simulate road conditions. The car is driven through a standard cycle of acceleration, braking, shifting, and cruising, all while remaining stationary. This test evaluates key systems including ABS, traction control, throttle response, gear engagement, hybrid transitions, and engine tuning. Sophisticated sensors and computers monitor hundreds of data points per second, ensuring the vehicle performs exactly as designed. Following the rolling test, the vehicle undergoes a headlight alignment and safety calibration station. Here, laser-guided systems measure the alignment of headlamps, and adjustments are made to meet both manufacturer and regional regulations. Advanced driver assistance systems such as lane keeping assist, adaptive cruise control, and forward collision warning are also calibrated at this point. This is accomplished using visual targets placed at known distances and angles in front of the vehicle, allowing cameras and radar units to learn their field of vision relative to the car's center line. Once these tests are complete, the vehicle proceeds to the water leak test booth, a sealed chamber equipped with an array of high-pressure water jets. For several minutes, water is sprayed at every angle, above, below, and from the sides, mimicking hurricane-force rain. Technicians inspect the cabin interior afterward for leaks, particularly around window seals, sunroofs, and door frames. Any sign of moisture sends the vehicle to a sealing team for immediate remediation and retesting. The car now moves into the final inspection area, often referred to as the white light tunnel. This zone is illuminated by intense, color-corrected lighting systems that reveal even the smallest defects in paint, fitment, and alignment. A team of inspectors walks around each vehicle, using mirrors to check lower panels, feelers to check panel gaps, and gauges to measure surface flushness. They assess the finish of paint, the gloss consistency, the evenness of door gaps, and the snugness of interior trim. Particular attention is paid to areas around weld joints, door hinges, and tailgate edges where minor misalignments can occur. Each inspector has the authority to flag the vehicle for any observed issue, no matter how small. Flagged cars are moved to a rework area where expert technicians resolve any concern before the vehicle can be released. Rework stations are not viewed negatively. They exist to ensure that every vehicle that exits the factory is indistinguishable from one that passed cleanly through all stages. After final inspection, the vehicle is prepared for delivery. Protective plastic sheeting is applied to painted surfaces and interior areas prone to contact during transport. The car is then driven to a shipping lot, where it is scanned into inventory and parked according to destination. Vehicles headed for domestic markets are grouped by dealership region and loaded onto transport carriers, while those bound for international markets are routed toward ports and loaded onto ships. The Honda factory's job may seem finished here, but in truth, its responsibility continues well beyond the factory gates. Each car's production data, including every torque value, software version, fluid fill level, and test result, is linked to its unique vehicle identification number and stored securely in Honda's manufacturing cloud. If an issue ever arises in the field, Honda can trace it back to the exact moment and operator involved in the car's creation. To witness the making of a Ford vehicle is to observe the evolution of industrial craftsmanship, a living embodiment of the assembly line system first pioneered by Henry Ford over a century ago, and refined today into a symphony of automation, digital intelligence, and human engineering. In modern Ford factories, like the Rouge Complex in Dearborn, Michigan, or the Oakville Assembly Plant in Ontario, production isn't simply about building cars. It's about orchestrating a precisely timed flow of materials, people, and machines that together transform raw components into advanced, drivable technology. The process begins long before the first bolt is turned or the first panel is stamped. The foundation of Ford's modern production system lies in rigorous planning and global coordination. Ford operates with a just-in-time and just-in-sequence supply chain strategy, meaning that materials and components arrive at the factory floor moments before they are needed. This eliminates the need for large stockpiles of inventory and increases the plant's flexibility to respond to changes in production schedules or model configurations. Planning starts with demand forecasting and order management. Using a centralized production planning system, Ford determines what models, trims, colors, and drivetrain variants will be built on any given day based on global dealer orders, regional demand patterns, and parts availability. This build mix is then converted into a master schedule that guides every action in the plant, from how robots are programmed, to which parts are loaded into which bins on which carts. At the heart of every Ford plant lies the stamping facility, where large rolls of sheet metal, primarily steel and aluminum, are cut and formed into individual body panels. These sheets arrive from external suppliers and are checked for thickness, flatness, and coating quality before entering the production line. Inside the stamping area, massive hydraulic or mechanical presses, sometimes up to 30 feet tall, use high tonnage force to shape the sheets into components such as hoods, roof panels, fenders, doors, and floor pans. Each stamping press contains tool and die sets, which are the sculpted steel molds that give shape to the metal. Changing these dies can take several hours on older systems, but Ford's modern plants use quick change tooling and automated die swapping cranes, allowing multiple model variants to be stamped in a single shift. Once stamped, each panel is inspected using automated vision systems and tactile measuring tools to ensure dimensional accuracy and surface quality. These stamped parts are then sent via conveyor or robotic shuttle to the next critical phase: body construction. In the body shop, robots dominate the floor. Here, the car's skeletal structure, called the body in white, is assembled from stamped panels. Using a combination of spot welding, MIG welding, and adhesive bonding, robots join together hundreds of individual panels to form a rigid structure that meets crash and durability standards. Each robotic cell is carefully synchronized, with arms moving in mirrored patterns to weld seams, attach reinforcements, and secure structural elements like the rocker panels and cross members. The entire body structure is periodically scanned with laser measurement systems, These 3D scanners create digital models of the assembled body to verify that it remains within tight tolerances. Even the smallest variation, fractions of a millimeter, could cause issues with later stages, such as door alignment or windshield fitting. If a body is found out of spec, it is automatically flagged and removed from the line for correction or further inspection. While the robots do the bulk of welding, human operators in the body shop play crucial roles. Some welds require access to tight spaces that robots can't easily reach. In addition, skilled technicians perform tactile inspections, feeling for uneven surfaces, sharp edges, or anomalies that a vision system might miss. They are also empowered to stop the line using an andon system, a visible alert mechanism that signals an issue requiring immediate attention, a practice inherited from lean manufacturing disciplines. Once the body is complete, it's sent to the paint shop, a sealed and environmentally controlled environment that is perhaps the most intricate and sensitive area of the plant. But before paint can be applied, the body must be cleaned, prepped, and protected. It first enters an electrodeposition tank, or e-coat bath, where it is submerged in a liquid anti-corrosion primer. An electric current causes this primer to bond uniformly to every surface of the body, inside and out, including hidden cavities where rust could otherwise form over time. After curing in an oven, the body moves into a multi-stage painting process. Robots apply layers of primer, color, and clear coat using electrostatic spray guns, which attract paint particles to the metal surface like a magnet. The advantage of this method is increased efficiency and reduced overspray, leading to lower paint consumption and a cleaner environment. Ford's paint booths are equipped with air filtration and humidity control systems to eliminate dust or contaminants that could mar the finish. At each stage, lighting conditions are precisely calibrated to reveal imperfections, and technicians are stationed throughout the booth to perform quality checks. If a blemish is detected, a run in the paint, an uneven finish, or a missed spot, the vehicle is diverted to a paint repair zone, where the affected area is wet sanded, resprayed, or polished by hand to meet Ford's appearance standards. After the final coat, the body undergoes a final curing process in a high-temperature oven to harden the paint and create a durable, glossy finish. The now fully painted vehicle shell, known as the trimmed body, advances to the general assembly line. This is the most labor-intensive section of the factory, where machines and humans collaborate closely. Unlike the body shop, where robots dominate, the general assembly area relies more heavily on human hands, precision tools, and ergonomic aids. The car body is mounted on a moving conveyor system known as a skillet line or friction drive platform, which carries the car through a series of workstations at a constant, carefully controlled speed. Assembly begins from the inside out. First, teams install insulation pads and sound deadening materials. Next, wiring harnesses, which form the car's electrical nervous system, are laid out and clipped into position along the floor, firewall, and side panels. Each harness contains dozens of connectors that will link to ECUs, lighting elements, climate controls, sensors, and powertrain systems. Proper routing and fastening of these cables are essential for both performance and safety, so visual checks and scanner-based validations are used at multiple points. Then comes the dashboard module, which is typically pre-assembled in a nearby subline. It includes the steering column, HVAC ducts, infotainment screen, and instrument cluster. This large component is inserted into the cabin as a unit using mechanical arms and then bolted into place. Seats, carpeting, interior trim panels, seatbelt retractors, airbags, and roof liners follow, each added in a precise order, with visual and tactile inspections performed continuously to ensure flawless fit and finish. Throughout this interior build process, Ford uses error-proofing tools such as torque-controlled wrenches, pick-to-light bins, and vision-guided assist arms. Every torque application is digitally logged. If a bolt is over or under-torqued, the system automatically halts the line and flags the issue. This traceability is vital, not only for quality assurance, but also for future diagnostics should the vehicle need service or become subject to a recall. Continuing from the general assembly line, the next transformative step in the creation of a Ford vehicle is the marriage of the painted body with the powertrain and chassis systems, a defining moment in every car's life on the line. As the body shell makes its way along the conveyor, the fully assembled engine, transmission, suspension, and front subframe approach from a lower parallel track. These components, built and tested in a separate sub-assembly area, are synchronized to arrive at the exact moment when the body reaches the marriage station. Here, specialized lifting systems raise the powertrain module from below while the body is gently lowered from above. Technicians, supported by robotic arms and torque-controlled tools, fasten the body to the chassis at critical mounting points. This precise alignment is essential. It determines the geometry of the suspension, the drivetrain angles, and even the behavior of noise and vibration through the cabin. Fuel lines, coolant hoses, drive shafts, brake lines, and wiring harnesses are then connected between body and chassis, integrating the mechanical and electrical systems into a unified vehicle. After the marriage, the vehicle receives its cooling system, air intake, and exhaust components, followed by fluids, including engine oil, brake fluid, transmission fluid, and coolant, all filled using automated dispensers that monitor volume, pressure, and flow rate. These filling stations ensure consistency down to the milliliter, and if there is any deviation from the programmed values, the system stops the process and flags the vehicle for investigation. With the engine installed and fluids topped off, the vehicle is now nearly complete. It receives its wheels and tires, which are pre-mounted, balanced, and matched to the specific trim and model variant. These are installed using torque monitoring impact wrenches, and the system logs each wheel's torque values in the vehicle's digital build record. Exterior components such as bumpers, lights, badges, grille assemblies, and mirrors are now added, bringing the vehicle's final form into view. At this stage, the car has all its physical components, but it still needs to come to life. The next section of the line is dedicated to initial startup and systems calibration. A technician connects the vehicle to a diagnostic console and performs the first ignition sequence. This process powers up the ECUs, activates safety systems, and starts the engine. Immediately, a flood of data is captured: oil pressure, engine RPM, voltage, emissions readiness, and more. The technician watches for warning lights, verifies software synchronization, and confirms that all onboard systems are responsive. If all readings are within specification, the vehicle advances to functional testing, where every major system, lights, brakes, steering, wipers, infotainment, HVAC, and electronic safety aids, is tested in a rapid, choreographed routine. Ford technicians use handheld devices and sensor panels to trigger functions and confirm their proper operation, all while the vehicle moves slowly along the inspection path. Any anomaly here diverts the vehicle to a diagnostics bay for further analysis. The production of a Tesla vehicle begins long before any car takes shape on the assembly line. Deep within the vast expanse of a Tesla Gigafactory, a meticulously orchestrated sequence of processes brings together raw materials, robotics, and human ingenuity to transform aluminum, lithium, silicon, and countless other elements into one of the most advanced electric vehicles on the planet. From the first bolt of sheet metal to the final pixel on the touchscreen interface, every component is born of a vision rooted in automation, precision, and sustainability. We begin with the raw materials that will ultimately form the structural skeleton of the car. Aluminum coils. These massive, industrial-grade aluminum rolls are delivered to the stamping facility in pre-cut widths and are carefully inspected for thickness consistency, surface finish, and chemical composition. Tesla predominantly uses high-strength aluminum alloys for many of its structural components due to their lightweight yet durable properties. These alloys are crucial to achieving Tesla's performance goals without sacrificing efficiency or safety. As each coil is unspooled, it is fed into a massive blanking press, a machine capable of cutting large sheets into specific dimensions called blanks. These blanks, often the size of a car door or hood, are prepped for the stamping process, where one of the most visually dramatic parts of the car's creation takes place. The stamping area, often housed in its own building due to the sheer vibration and noise, is where enormous dies, precision-engineered molds weighing several tons, shape these blanks into panels that will form the body-in-white structure of the car. Each die is lowered into a stamping press, often a servo-driven press with forces exceeding 5,000 tons. These machines exert immense pressure in milliseconds, forming the aluminum blank into complex geometries. Multiple stages of stamping may be needed for a single panel, including draw, trim, pierce, and flange operations. After stamping, robotic arms lift and transfer the formed panels onto conveyor belts, directing them to a quality inspection zone where laser scanners and human inspectors check for warping, stress marks, or micro cracks. Any deviation from tolerance can compromise fit or function and is promptly rejected or reworked. While the body panels are being shaped, another process begins deep inside the battery cell manufacturing area. Tesla, being vertically integrated, produces many of its own lithium-ion battery cells. Raw materials such as nickel, cobalt, manganese, and lithium carbonate are transported into specialized mixing tanks where they undergo slurry formation. These slurries are spread onto copper and aluminum foils, which are then dried in a vacuum oven to form electrodes. Once the electrodes are prepared, they are calendared, flattened to precise thicknesses, and wound or stacked into cylindrical, pouch, or prismatic cells depending on the vehicle model. Each cell is filled with electrolyte solution and hermetically sealed in a dry room to prevent moisture contamination, which could compromise safety or performance. These cells are then loaded into battery modules using robotic pick-and-place arms, which align and connect the terminals with extreme accuracy. The modules are assembled into packs, which include integrated cooling channels, structural support, and electronic control units. These battery packs will eventually be installed into the vehicle's underbody, providing both power and structural rigidity. Back in the body shop, the stamped aluminum panels are robotically welded and riveted together to form the body in white, the term for the car's skeletal shell before any paint or interior components are added. Tesla employs a combination of laser welding, spot welding, and structural adhesive bonding to fuse panels together with minimal distortion and maximum strength. Hundreds of robotic arms suspended from overhead gantries work in synchronized motion, welding, clamping, positioning, all choreographed with software that can adjust in real time based on tolerances and feedback. Laser scanners constantly monitor joint integrity and positional accuracy, ensuring that each weld is correctly formed and precisely located. The body in white at this stage is a gleaming raw aluminum shell, unpainted but fully formed, with all major exterior panels in place, including doors, hoods, and trunk lids, which are often removed and processed separately for better access and quality control. The next destination for the body is the paint shop, one of the most complex and environmentally controlled areas of the entire factory. Before painting can begin, the aluminum body must undergo a chemical pre-treatment process that removes oils, residues, and impurities. This is achieved by submerging the body in a series of baths, alkaline cleaners, deionized water rinses, and ultimately a zirconium or phosphate-based conversion coating that promotes adhesion and corrosion resistance. After drying in an oven to eliminate residual moisture, the body moves into the electrocoating tank, or e-coat stage. Here, the entire shell is submerged in a bath of electrically charged paint particles, which uniformly coat every crevice and interior cavity, ensuring anti-corrosion protection even in areas never visible to the customer. The body is then baked in a curing oven to harden the coating and prepare it for the next layers of paint. The painting process involves multiple coats: primer, base coat, and clear coat. Each coat is applied in sealed spray booths using high-precision atomizing robots, which follow programmed trajectories to ensure even coverage. Advanced electrostatic spray techniques are used to minimize overspray and improve efficiency. After each coat, the vehicle passes through a series of flash and bake ovens to dry and cure the paint, creating the high-gloss finish Tesla vehicles are known for. Once painting is complete, the body heads to the general assembly area, where it begins to transform from an empty shell into a fully operational vehicle. But before any parts are installed, the body undergoes another round of rigorous inspections. Laser alignment systems, gap and flush measuring tools, and robotic probes verify dimensional consistency across every surface. Any discrepancies are flagged and corrected before proceeding. Simultaneously, thousands of components are arriving from various sub-assembly lines and suppliers, including the interior trim, seats, dashboards, glass, wiring harnesses, and powertrain modules. These parts are delivered using automated guided vehicles, AGVs, that navigate the factory floor using embedded magnetic strips or LiDAR-based systems, ensuring just-in-time delivery with minimal human handling. The interior assembly begins with the installation of wiring harnesses, which are laid throughout the vehicle like a nervous system. These harnesses, containing kilometers of wire, are clipped into designated paths along the floor, pillars, and roof. Robots and human technicians work together, ensuring connectors are correctly routed and terminals are securely fastened. Next, the HVAC components, dashboard structure, and infotainment systems are installed, followed by airbags, sound insulation, and seat frames. At each step, torque-controlled tools and digital confirmation systems ensure that every fastener meets the required specification. The vehicle's panoramic glass roof, a signature element of Tesla's design language, is then lowered into place using vacuum suction lifters and laser-guided alignment tools. A two-part adhesive is applied by robotic nozzles to create a watertight seal. The doors, previously processed separately, are reattached and calibrated to ensure perfect alignment and smooth operation. Tesla's frameless door design and automatic opening features require particularly tight tolerances and sensor calibration. With the interior taking shape, the vehicle proceeds to powertrain integration, where the battery pack, assembled and tested in a parallel process, is lifted by robotic jigs and bolted into the vehicle's underbody using a sequence of torque-controlled actuators. The drive units, whether dual or tri-motor, are then installed onto the front and rear subframes, connected via suspension arms and motor mounts that are pre-aligned using precision fixtures. With the battery pack securely mounted and the drive units in position, the vehicle is now ready to undergo one of the most critical transitions in the entire manufacturing process: electrical and software activation. While the car may appear nearly complete, it is still lifeless. No lights, no screen activity, no sensor communication. This stage, often referred to as initialization, is where the vehicle essentially takes its first breath. A technician connects a diagnostic interface to the vehicle's central computer, usually via a secure data port under the dash, and uploads the foundational firmware that activates the vehicle's electronic control units, or ECUs. Each Tesla contains dozens of ECUs distributed throughout the chassis, responsible for everything from motor control to autopilot systems, battery thermal regulation, infotainment, and safety monitoring. Tesla's approach to software architecture is notably centralized compared to traditional automakers. Instead of relying on fragmented systems developed by various suppliers, Tesla has developed an in-house software stack that enables over-the-air updates, real-time diagnostics, and direct integration between mechanical systems and the vehicle's neural net. Once the firmware is loaded, a cascade of subsystems begins to power on. The touchscreen illuminates for the first time. The instrument cluster boots up. Cameras begin streaming to internal diagnostics. Every sensor, switch, and relay goes through a self-check process that verifies communication with the vehicle's central gateway. Any issues, such as a disconnected wire, a miscalibrated radar unit, or a sensor failure, are immediately logged for remediation. At this stage, even something as minor as a single LED malfunction will halt the progression until it's resolved. Next, attention turns to calibrating the advanced driver assistance systems. Tesla's autopilot suite relies heavily on an array of forward, rear, and side-facing cameras, ultrasonic sensors, and radar or LiDAR, depending on the model and hardware iteration. These units must be precisely aligned within the bodywork to ensure accurate environmental perception. Calibration is not just mechanical, but also algorithmic. As the vehicle is rolled into a controlled calibration zone, a series of reference panels, patterns, and 3D markers are placed around the car. Cameras are activated, and software compares live imaging data against known coordinates to fine-tune the visual input. The system will not pass if even a single camera is slightly skewed or obstructed. Following this, the wheels and tires are mounted, another process where automation and precision intersect. Each wheel assembly, comprising the tire, alloy rim, TPMS sensor, and balancing weights, is prepared in an adjacent sub-assembly cell. Robotic arms select the correct wheel variant depending on trim level and mount it onto the vehicle's wheel hub using torque-monitored tools. Once installed, the wheels are not yet fully ready for the road. They must be aligned. Wheel alignment takes place on a dedicated platform, where laser or camera-based alignment tools measure caster, camber, and toe angles in real time. Adjustments are made on the spot using robotic wrenches that turn suspension bolts until readings fall within micrometer level tolerances. Proper alignment is vital, not only for performance and safety, but also for autopilot accuracy, as steering bias or drift could interfere with the vehicle's self-driving capabilities. Now we arrive at one of the most impressive parts of Tesla's assembly process: final assembly verification and end-of-line testing. This begins with a full-body water intrusion test. The completed vehicle is driven, or in some cases, automatically transported, into a sealed chamber known as the water test booth. High-pressure nozzles blast the car from all directions, simulating rain, puddle splashes, and pressure washing. Sensors inside the cabin monitor for even the slightest moisture intrusion. Any leak, even a trace around the door seals or underbody joints, results in a stop and targeted repair. Once the vehicle passes the water test, it moves into dynamic testing. But before that can begin, it must first pass a rolling road diagnostic check. The vehicle is positioned on a set of rollers that simulate driving conditions. Here, Tesla technicians run through a wide range of operational checks. Motor response is tested across a variety of simulated terrain profiles. Regenerative braking systems are evaluated to confirm energy recovery rates match expected values. HVAC systems are activated to check for proper airflow, temperature regulation, and acoustic performance. Inside the cabin, the touchscreen interface undergoes a systems integrity test. Each menu, function, and button is activated in sequence. The infotainment system is tested for connectivity to Tesla's software servers. Navigation modules are initialized. Bluetooth and Wi-Fi antennas are pinged. Microphones and speakers are checked for distortion or static. The cabin camera, located near the rearview mirror, is tested for focus and response to light changes. The glove box, front latch, trunk motors, and window regulators are also checked for proper operation and speed. After static diagnostics, the vehicle is finally ready for its low-speed dynamic test. On-site test tracks, usually located adjacent to or within the Gigafactory premises, allow each vehicle to undergo a short but comprehensive road test. The driver is usually a trained Tesla technician who runs the car through a prescribed routine: acceleration from 0 to moderate speeds, emergency braking, tight cornering, and high-speed lane changes. This test evaluates suspension response, noise levels, steering feel, and drivetrain behavior under real load conditions. The vehicle's software continues to log performance data throughout the drive, flagging any anomalies. After returning from the test track, the car enters the final visual inspection area. Here, a team of human inspectors armed with light panels, bore scopes, and digital checklists reviews every visible surface inside and out. Paint quality is scrutinized for orange peel texture, swirl marks, or dust nibs. Panel gaps are measured by hand and with laser gauges. The interior is inspected for material alignment, stitching accuracy, and uniform texture. Every single button, vent, trim piece, and fixture is physically touched and verified. If the vehicle passes this multi-layered gauntlet of inspections, it moves into what's known as pack out, the final preparation area before shipment. Here, the car receives its VIN label, ownership documentation, and destination configuration. This is where region-specific software settings, navigation maps, and language preferences are loaded. The final battery charge is administered, usually to around 90%, before the vehicle is powered down and prepared for transport. Each Tesla is now ready to leave the factory, but even this step is a study in logistical precision. Automated systems coordinate the movement of completed vehicles from the final inspection bay to outbound logistics. Depending on destination, the vehicle may be loaded onto a covered rail car, placed into a secure car carrier, or transferred to a nearby delivery hub. RFID tags embedded in the vehicle identify it to tracking systems that monitor its journey to the customer. It is important to note that Tesla's manufacturing ethos is grounded in continuous improvement. Unlike traditional automakers that rely on annual model cycles, Tesla frequently changes its assembly lines in real time, updating hardware or processes based on production learnings, user feedback, and software improvements. This philosophy means that even within the same week, two identical models may have subtle differences in componentry, firmware version, or assembly methods. These continuous upgrades are made possible by Tesla's heavy reliance on vertical integration and factory-level data analytics. Every torque wrench, sensor, robot, and diagnostic station feeds data into a centralized factory control system. Engineers analyze this data daily, making adjustments to improve efficiency, reduce rework rates, and enhance vehicle quality. This feedback loop between digital twin modeling, live production, and field performance is one of the reasons Tesla has been able to scale quickly while maintaining product innovation. With the vehicle now fully assembled, inspected, and approved, it embarks on the final leg of its journey: delivery to the customer. Whether arriving at a showroom, a regional distribution center, or directly to a driveway via Tesla's direct delivery program, the finished product represents not just a vehicle, but the culmination of thousands of interconnected systems working in harmony, each with millisecond-level precision, each tuned for performance, safety, and the future of mobility. Once a Tesla vehicle has cleared its final inspection and receives its shipment authorization, the journey from the Gigafactory to the customer begins. Unlike conventional auto manufacturers, which often rely on third-party dealership networks and extensive warehousing chains, Tesla's direct-to-consumer delivery model has radically simplified and streamlined this phase. Yet, behind that apparent simplicity lies a highly coordinated logistical infrastructure, optimized to handle the massive volume of vehicles produced daily across multiple global factories. At this stage, the vehicle is routed into a specialized outbound logistics yard, a designated section of the Gigafactory site, or an adjoining facility engineered specifically for the staging, sequencing, and transportation of finished vehicles. Each car is tagged with a digital shipping label that contains its vehicle identification number, model variant, color, wheel configuration, destination, and special instructions such as left-hand versus right-hand drive. This digital manifest is cross-referenced with Tesla's centralized logistics control software, ensuring that each car is placed into the correct regional batch for dispatch. Automated tug vehicles, similar to those used in airport ground operations, tow trailers of Tesla vehicles into position. If the vehicle is destined for domestic delivery, it is typically loaded onto a car carrier truck designed to hold 7 to 10 units. These carriers are scheduled to depart in tightly timed intervals, with software routing each truck for the most efficient delivery path based on real-time traffic, weather, and destination inventory levels. For international shipments, the process shifts slightly. Vehicles bound for overseas markets are loaded onto rail cars or container haulers that transport them to port facilities. At the port, the vehicles are driven onto roll-on/roll-off ships, a type of cargo vessel with built-in ramps and internal decks specifically designed for transporting cars. Each Tesla is parked and secured inside the vessel, often alongside other vehicles of the same batch, in a configuration that minimizes offloading time upon arrival. Throughout this journey, every vehicle remains digitally visible to Tesla's logistics team. GPS tags, onboard cellular connectivity, and carrier integration systems allow real-time tracking from the moment the vehicle leaves the plant to the moment it is delivered to the end customer. This level of transparency enables Tesla to forecast delivery windows with a high degree of accuracy and proactively resolve issues like weather delays or customs bottlenecks. Meanwhile, Tesla's delivery centers and service hubs are preparing to receive the vehicles. These locations, often converted warehouse spaces or minimalist showrooms, act as regional fulfillment points. Upon arrival, each vehicle undergoes a final pre-delivery inspection. This includes checking tire pressures, topping off windshield washer fluid, confirming that the software version is current, and ensuring the paint and interior remain in pristine condition. The protective coverings applied during shipment, such as plastic seat covers and foam door guards, are removed, and the car is detailed for presentation. If a customer has opted for Tesla's home delivery option, the vehicle may be dispatched from the delivery center directly to the buyer's driveway using either a flatbed or a mobile technician. Tesla's minimalist approach to delivery day often involves minimal paperwork, since much of the ownership transfer process is handled digitally ahead of time. Customers sign final documents electronically, receive a tutorial on using their new vehicle via the in-car interface or mobile app, and are given access to Tesla's expansive digital support ecosystem. But delivery is not the end of the story. It's merely the handoff point between manufacturing and long-term ownership. Tesla's commitment to post-production support is tightly integrated into its digital platform. The same software and hardware systems that facilitated the car's birth on the factory floor now serve as tools for its ongoing evolution. Over-the-air updates are one of the most defining characteristics of the Tesla ownership experience, and they depend on a robust ecosystem of remote diagnostics, data collection, and machine learning feedback loops. Every Tesla on the road constantly reports anonymized performance data back to Tesla's servers. This includes battery health, motor efficiency, navigation anomalies, autopilot behavior, sensor readings, and even software bugs. Engineers at Tesla's headquarters use this data to refine algorithms, push updates to correct inefficiencies, and enhance safety features, all without the owner needing to visit a service center. This dynamic software lifecycle, enabled by the tightly coupled manufacturing and software teams, makes Tesla vehicles unique in their ability to improve long after leaving the factory. Meanwhile, Tesla's service infrastructure continues to grow alongside its production volume. Instead of relying entirely on traditional service centers, Tesla employs a mobile service strategy wherever possible. These service vans are equipped with diagnostic tools, replacement parts, and certified technicians who can perform a wide range of repairs or updates at the customer's location. The ability to diagnose and even preemptively fix issues before they affect the driver is rooted in the precision and data fidelity achieved during the original manufacturing process. Looking back toward the factory, it's important to understand how Tesla's architectural philosophy supports this entire life cycle. Every Gigafactory is designed not just to build vehicles, but to serve as a data hub, a testing ground, and a self-improving machine. These plants are built with flexibility in mind, using modular assembly lines that can be reconfigured on the fly. Instead of fixed conveyor belts, Tesla often uses autonomous mobile robots and smart material flow systems that can reroute components or vehicles as production needs change. The Gigafactory floor is not one continuous line, but a series of interconnected stations. Each one is equipped with sensors, machine vision, and feedback modules that report into a central factory operating system. This system not only tracks current production metrics, but also simulates process optimizations. For example, if a torque reading at a robotic arm consistently falls within the low-end threshold, engineers can be alerted and update the robot's behavior before a quality deviation even occurs. This predictive control approach reduces downtime and increases first-pass yield, meaning more vehicles pass inspection on the first try without needing rework. Vertical integration plays a critical role in making this system work. Tesla doesn't just assemble parts, it manufactures many of them. From battery cells to electric motors, from infotainment chips to firmware code, Tesla has brought traditionally outsourced operations in-house. This reduces dependency on suppliers, shortens feedback loops, and allows the company to innovate rapidly. For instance, if a new battery chemistry is developed in Tesla's R&D lab, pilot-scale production can begin almost immediately within a section of the existing Gigafactory, without the need for third-party approval or infrastructure overhaul. Even Tesla's supply chain reflects this philosophy of speed, control, and adaptability. Critical materials like lithium, nickel, and cobalt are sourced through long-term contracts with mining operations. And in some cases, Tesla has invested directly in extraction or refinement operations. These materials are routed directly to gigafactories or regional production hubs, bypassing many of the bottlenecks that affect traditional automakers who rely on complex supplier tiers and international freight forwarding. This system is further enhanced by Tesla's real-time digital twin architecture, a virtual replica of the entire manufacturing process. Every machine, part, and process is mirrored in a digital environment that can simulate disruptions, forecast efficiency gains, and run hypothetical scenarios. Want to test how a new weld technique might affect throughput? The digital twin can simulate that change in minutes, allowing engineers to make data-backed decisions that translate directly into physical adjustments. Through all of these layers, physical infrastructure, software integration, vertical manufacturing, and delivery logistics, Tesla has redefined what modern automotive production looks like. It's not just about building cars, it's about building a system that builds itself smarter with every iteration. Every vehicle produced feeds data back into this system. Every manufacturing anomaly becomes a learning opportunity. Every software update enhances not just the product, but the factory's ability to produce the next one even better. What this means is that the Gigafactory isn't a static building. It's a living organism, a self-correcting, self-improving entity designed not only to produce cars, but to redefine what a car even is in the age of autonomy, electrification, and artificial intelligence. And at the center of this vision lies a carefully choreographed dance of machinery, people, data, and innovation, all working in harmony to create not just a vehicle, but a new standard for the global auto industry. Inside a Tesla Gigafactory, perhaps the most mesmerizing and defining visual is the near-symphonic choreography of robots working in harmony. Tesla employs tens of thousands of industrial robots across its global facilities, many sourced from automation giants like KUKA and FANUC, and many others developed in-house. But these aren't the slow, single-arm welders of traditional auto plants. These are high-speed, multi-axis machines operating in tightly coordinated clusters that resemble mechanical dance troupes, fast, precise, and relentlessly efficient. The bulk of these robots are deployed in the body shop, where raw stamped panels are joined to form the body in white. Here, multiple robot arms work within inches of one another, one positioning a panel, another applying structural adhesive, and a third completing a weld, without ever colliding. This level of spatial awareness is made possible by a digital supervisory system that orchestrates each motion path in microseconds. Each robot is fitted with a suite of sensors, including force feedback, proximity detectors, and sometimes even cameras, allowing them to adapt slightly if a panel is marginally misaligned or a weld point needs micro-adjustment. In many production cells, Tesla has implemented what are known as friction stir welding units, robots capable of joining aluminum panels without melting them. This technique, originally developed for aerospace manufacturing, uses a high-speed, rotating tool that generates frictional heat to soften and fuse materials without introducing impurities or thermal distortion. It results in stronger joints and is especially effective for joining thick battery pack casings or high-stress structural nodes. But Tesla's automation does not end at the mechanical level. Surrounding the physical robots is a vast digital control infrastructure powered by machine learning algorithms that analyze every torque value, weld voltage, and robot movement. These systems compare every single action against historical data to identify patterns that may indicate future faults. For example, if a particular welding arm shows a slight uptick in motion latency or current draw, the system can schedule predictive maintenance before a full failure occurs. This predictive maintenance loop dramatically increases uptime and reduces unexpected halts in the production line. Complementing this robotic workforce is a carefully integrated human team. Contrary to the misconception that gigafactories are purely robotic, Tesla maintains a robust human workforce in areas where judgment, dexterity, or problem solving are still superior to automation. For instance, interior trim installation, particularly tasks involving soft materials like Alcantara, stitched leather, or delicate wiring, still relies on trained technicians who can feel for correct tension, align materials by eye, and make subtle corrections during fitment. Human workers are also essential during final inspection, dynamic testing, and exception handling. If a part doesn't meet specifications, or if a software glitch prevents a subsystem from booting, it's often a human specialist who diagnoses and resolves the issue. These employees are equipped with digital tablets linked to Tesla's internal manufacturing cloud. They receive live data feeds from the vehicle's onboard sensors and can pull up schematics, tolerances, and previous production history in seconds. Every fix they apply, every note they enter, becomes part of that car's digital footprint, a log that follows it forever. even into post-sale diagnostics. Tesla's approach to worker efficiency is also shaped by ergonomic engineering and cognitive load optimization. Workstations are designed to reduce repetitive strain injuries with tool arms that balance heavy equipment and lift assists for placing components. Augmented reality overlays are sometimes used during training phases, projecting digital guides onto surfaces to help new employees understand complex assemblies. Rotational schedules ensure workers shift between physically demanding tasks and more routine duties, helping prevent fatigue-related errors. As we dig deeper into the brain of the Gigafactory, we arrive at what is perhaps Tesla's greatest long-term differentiator: the use of artificial intelligence, not just in the vehicles, but within the factory itself. Tesla doesn't merely automate individual machines, it trains its factories to optimize themselves. This is achieved through a combination of real-time data ingestion, cloud-based analytics, and reinforcement learning loops. Let's take an example from the paint shop. Traditionally, robots follow predefined spray paths based on CAD data. However, Tesla trains its painting robots using vision-based systems that analyze each body shell in real time for curvature, panel orientation, and gap uniformity. This data informs dynamic adjustments to spray trajectory, nozzle pressure, and stroke timing. The result is more uniform coating, fewer touch-ups, and improved long-term finish durability. Or consider battery pack assembly. Each cell inserted into a module is monitored for voltage, internal resistance, and capacitance. Tesla uses this data to build a profile of every module's thermal characteristics. If a pattern of abnormal cell degradation is observed in the field, engineers can trace it back to the exact production batch, process variables, or even environmental conditions at the time of assembly. This data loop enables retroactive improvements to manufacturing conditions and helps refine pack longevity models for future software updates. One of the more futuristic systems Tesla is rolling out across its newer Gigafactories involves swarm intelligence for material transport. Rather than fixed conveyor systems, Tesla uses fleets of autonomous mobile robots that navigate the factory floor using SLAM algorithms. These robots aren't programmed with fixed paths. They learn optimal routes in real time, adapt to obstacles, and communicate with one another to avoid collisions or bottlenecks. This approach allows the factory layout to be more modular and reconfigurable, supporting agile production and faster adaptation to new models or variants. Equally fascinating is Tesla's use of simulation environments for factory operations. Entire sections of the Gigafactory are mirrored in a digital twin, an exact 3D replica of the physical space and its processes. Engineers can run simulations to test new workflows, evaluate machinery upgrades, or even plan how to integrate a new vehicle platform without ever disrupting the live production line. If a simulated robot collision is detected, the system can suggest path modifications or sequence changes before real-world implementation. This same philosophy extends to Tesla's use of custom silicon chips. While best known for its full self-driving computer, Tesla also designs specialized hardware for internal factory use. These include image recognition chips optimized for high-speed defect detection, edge computing units for data processing at the machine level, and embedded control systems that allow more precise energy regulation in welding and curing ovens. This level of hardware customization provides Tesla with granular control over quality, energy efficiency, and process speed. Another compelling layer of Tesla's factory evolution involves environmental engineering. Every Gigafactory is designed with sustainability as a core tenet. Rooftop solar arrays, on-site water recycling systems, and battery-powered internal logistics vehicles are just some of the components contributing to closed-loop manufacturing. The energy used to produce each Tesla vehicle is increasingly being sourced from renewable systems within the facility itself, dramatically lowering life cycle carbon emissions. Tesla's focus on vertical integration again becomes critical here. When energy systems, battery chemistry, robotics, and software all originate from the same corporate ecosystem, coordination becomes exponentially easier. Design tweaks to the battery casing, for example, can immediately inform changes to the casting molds, welding fixtures, or software-based thermal models, without the friction of cross-company coordination. Perhaps the most emblematic symbol of this holistic integration is Tesla's gigacasting machines. These are among the most powerful aluminum die casting machines in the world, capable of creating entire underbody sections as a single solid piece. These machines, designed in partnership with Adidra, reduce the number of parts in the vehicle's chassis from hundreds to just a few, eliminating fasteners, reducing weight, and improving crash performance. Integrating such massive components into the production line requires not just physical reconfiguration, but software integration, supply chain alignment, and real-time QC adaptation, all of which Tesla is uniquely positioned to manage in-house. As we look at the sum of all these systems, robotics, AI, digital twins, human-machine interfaces, gigacasting, and energy-conscious infrastructure, it becomes clear that the Tesla production process is not simply a variation on traditional automotive manufacturing. It is an entirely new operating system for building cars. A platform, not just a plant. A fusion of machine intelligence, predictive analytics, physical innovation, and agile design thinking, all operating under a single cohesive philosophy. The Tesla Gigafactory isn't just where vehicles are built. It's where ideas are born, tested, scaled, and refined in real time. Where the boundary between hardware and software dissolves. Where every sensor, every weld, and every decision feeds back into a growing repository of knowledge that powers the next generation of vehicles, robots, factories, and systems. One of the most disruptive engineering breakthroughs in Tesla's modern manufacturing playbook is the integration of the structural battery pack, a complete rethinking of how the battery, chassis, and underbody of the vehicle work together. In traditional automotive design, the battery pack is a standalone component, an energy container bolted to the car's underbody. But in Tesla's structural pack architecture, pioneered with the 4680 battery format, the battery no longer rides beneath the structure, it becomes the structure. To understand the scale of this shift, we first need to explore the 4680 cell itself. Named for its dimensions, 46mm wide and 80mm tall, the 4680 cylindrical lithium-ion cell represents a significant departure from the older 2170 and 18650 formats. It offers 5 times the energy, 6 times the power, and reduces the cost per kilowatt hour significantly. But it's not just the size that matters, it's how the cells are built and what they enable downstream in manufacturing. Each 4680 cell is designed to support tabless internal architecture. In conventional cells, current must travel through a tab, a narrow conductor that can create resistance and heat. In Tesla's tabless design, the entire edge of the rolled electrode acts as a current collector, enabling more uniform heat distribution and higher current throughput. This drastically reduces internal resistance, improves efficiency during charge and discharge, and simplifies thermal management, a critical benefit when assembling high-density battery modules. These cells are produced in a vertically integrated line that starts with electrode slurry mixing, followed by coating, calendaring, cutting, and winding, all performed under strict environmental control. The wound jelly rolls are inserted into steel canisters, filled with electrolyte, sealed by laser welding, and then aged, tested, and sorted. What's remarkable is that Tesla's battery lines are not just production machines, they are learning machines. Each stage of battery cell production is heavily instrumented, with sensors that track viscosity, coating uniformity, line tension, and thermal behavior. These metrics feed back into AI-driven quality control systems that adapt in real time, reducing scrap rates and improving yield without requiring line shutdowns. Once the cells are complete, they are no longer assembled into modules as in traditional EVs. Instead, Tesla places them directly into the structural battery pack housing, eliminating intermediary module structures. This pack is a part of the vehicle's load-bearing frame, not an add-on. The cells are bonded in place using structural epoxy, and this bonded matrix provides rigidity akin to an aircraft's wing box design, a technique borrowed from aerospace engineering. A critical enabler of this approach is the use of high-performance structural foams and thermal adhesives. These materials serve multiple functions simultaneously. They manage vibration and noise, conduct heat away from the cells to integrated cooling loops, and crucially, form part of the vehicle's crash energy management system. During side or front impacts, the structural battery pack helps distribute forces across a wider area, reducing localized deformation and improving occupant safety. In the Gigafactory, structural pack assembly is a distinct line, physically separate from standard battery operations due to its unique tooling requirements. Cells are loaded into the pack casing using high-speed robotic insertion machines. Adhesive dispensing systems apply precisely metered quantities of two-part epoxy at high pressure. Once cells are in place, the entire structure is cured in massive industrial ovens that bring the adhesive to full mechanical strength. After cooling, the pack undergoes precision machining to create interfaces for the drive unit, seat mounts, and body attachment points. What results is not just a battery, it's a central element of the vehicle's physical frame. The top of the pack often serves as the interior floor of the cabin. The bottom, reinforced by ribbed aluminum or composite materials, acts as the underbody and aerodynamic tray. By combining energy storage, structural support, and crash safety into a single unit, Tesla eliminates dozens of separate components, reducing mass, simplifying manufacturing, and slashing costs. Now, integrate this with another innovation, gigacasting. Tesla's use of giant aluminum die casting machines to form the front and rear underbody sections of its vehicles is nothing short of revolutionary. These Edura Giga Press machines, weighing over 400 tons and applying clamping forces in the range of 6,000 to 9,000 tons, can create entire frame sections as a single cast. Instead of welding together hundreds of stamped components, Tesla now forms massive structural elements in one shot, lighter, stiffer, and far faster to produce. When the front and rear castings are combined with the central structural battery pack, Tesla essentially builds the entire underbody of a vehicle using just 3 large parts. These unibody trios replace what was once over 300 parts in older chassis architectures. This not only reduces complexity and assembly time, but also minimizes the number of suppliers, welds, fixtures, and potential quality defects. Each casting is inspected via X-ray and ultrasonic imaging to detect porosity, cracks, or incomplete fills. Any anomalies are rejected and remelted, maintaining a closed-loop aluminum recycling system. This radical simplification also redefines how the rest of the car is built. Traditional automotive factories are organized around a highly linear body-in-white process, frame construction, then floor pan, then underbody integration. Tesla's method is more like assembling a modular aircraft, where large sub-assemblies are brought together at fewer, more tightly controlled junctions. This allows Tesla to create more compact factories with faster cycle times and fewer workers per unit produced, metrics that directly impact capital efficiency and return on investment. To support these next-generation designs, Tesla continues to invest heavily in materials science research, much of it focused on high-strength aluminum alloys, advanced polymers, and die-casting feedstock refinement. The development of proprietary aluminum alloys that combine excellent flow characteristics in casting with high tensile strength post-treatment is a crucial part of making gigacasting work. These alloys must cool evenly, avoid brittleness, and withstand both crash loads and environmental exposure over time. In parallel, Tesla is exploring dry electrode manufacturing for future battery lines, a technique that eliminates the solvent-heavy coating and drying stages currently used in electrode production. Dry electrodes can be applied directly to the current collector using pressure and heat, significantly reducing energy consumption, production footprint, and cost. This aligns with Tesla's vision for more sustainable, vertically integrated gigafactories, ones that consume fewer resources per gigawatt hour and can be rapidly scaled in new geographies. Indeed, Tesla's goal is not just to build more cars, it's to scale manufacturing like a technology company, not an industrial one. This means shorter ramp-up times, smaller capital expenditures per unit of output, and a globally unified software-hardware stack that can be deployed anywhere in the world with minimal localization. Future gigafactories, like those planned in Mexico and India, are being designed with these structural pack and casting concepts at their core, meaning they won't just produce the next generation of Tesla vehicles, they will be born already optimized for speed, simplicity, and flexibility. This systems thinking extends even further into factory floor layout and material flow logistics. With fewer total parts, Tesla can implement straighter, more continuous material pathways, reducing the need for kitting, buffering, and material staging. Instead of having dozens of sub-assembly lines feeding hundreds of components, Tesla can deliver entire modules, like castings or packs, straight to the marriage station, where the vehicle begins to take its final form. This layout change reduces floor space, lowers error rates, and improves throughput. It also allows for greater software simulation of factory dynamics. When each vehicle only passes through 30 or 40 production cells, rather than 200 or 300, it becomes computationally feasible to simulate the entire factory in real time. AI-based systems can then test flow changes, balance labor loads, and reroute production if a bottleneck emerges, all before any change is implemented on the floor. The result is a self-learning, self-optimizing factory capable of adapting to demand shifts, supplier disruptions, or design updates faster than legacy automakers can retool a single line. All of this innovation, structural batteries, 4,680 cells, gigacasting, and software-first factories converges into a clear strategic objective: build more cars, better and faster, with fewer people and lower capital costs per unit. It's not about squeezing the last drop of efficiency from legacy systems. It's about replacing those systems entirely. And the boldness of that approach is why Tesla's manufacturing story remains one of the most closely watched industrial transformations of the 21st century. Inside the sleek, meticulously organized production halls, where Lexus vehicles are brought to life, craftsmanship meets cutting-edge automation in one of the most refined automotive manufacturing processes in the world. The journey of a Lexus begins not on the factory floor, but in the minds of engineers, designers, and master craftsmen known as Takumi. These artisans, with decades of experience, help shape the philosophy of quality and precision that defines every Lexus model. Before any physical materials are touched, the vehicle undergoes countless hours of design and digital simulation. Designers model each contour and surface using advanced CAD software, ensuring aerodynamics, aesthetics, and structural integrity are in harmony. Simultaneously, engineers plan out the vehicle's underlying architecture, the chassis, drivetrain, suspension system, and electronic infrastructure, all of which must integrate seamlessly in the final product. Once virtual models and prototypes are validated through digital stress testing and aerodynamic simulation, the blueprint is ready for translation into physical production. Raw materials for Lexus vehicles are sourced globally but meet stringent internal quality requirements. The main material used in the body is high tensile steel, although aluminum and lightweight composites are becoming increasingly common, especially in performance or hybrid models. Steel coils arrive at the plant in massive rolls and are carefully inspected for surface defects, strength, and elasticity. These coils are then unrolled and fed into precision cutting machines. Automated laser cutters slice the sheets into individual panels, doors, roofs, hoods, and side walls, each shaped with millimeter accuracy. These panels then undergo a series of progressive stamping operations. Gigantic hydraulic presses weighing several hundred tons pound each steel sheet into its designated shape using specialized dies. These dies are meticulously engineered and periodically recalibrated to maintain tolerances as tight as a fraction of a millimeter. During stamping, features like creases, curves, and reinforcement ribs are embedded directly into the metal, contributing both to design and structural integrity. The next stage is body-in-white assembly, where the vehicle's skeletal structure begins to take shape. Robotic arms equipped with weld guns perform thousands of spot welds per car, joining the stamped panels together into a rigid, seamless shell. Lexus factories often employ laser welding for specific areas like roof joints or pillars, achieving a cleaner finish and stronger bonds than traditional methods. A select group of highly trained technicians also perform manual welding in hard-to-reach areas, ensuring consistency across every build. Cameras and sensors continuously monitor the alignment of every panel to detect even the smallest deviations in fit or finish. With the raw body now assembled, it enters the paint shop, a controlled environment with extremely high cleanliness standards. Prior to painting, the body is submerged in an electrodeposition tank, where it's coated with a rust-inhibiting primer using an electric charge to bind the molecules to the steel. This anti-corrosion step is essential for longevity. After that, the car body passes through an automated sanding and cleaning line to prepare the surface for color application. Paint is applied in multiple coats: primer, base coat, and clear coat, using robot sprayers that mimic human wrist movements for a natural, even finish. Each paint layer is flash dried in curing ovens set to precise temperatures, and between each layer, the body is inspected under UV and white light to catch any inconsistencies or inclusions. Lexus offers a range of colors, but each hue is carefully developed to interact with lighting and body shape in a specific way. The final clear coat is cured in a high-temperature bake oven, after which the body is cooled slowly to prevent microcracking or warping. As the painted shell makes its way to general assembly, the mechanical heart of the Lexus is being prepared in parallel. Engine blocks, transmissions, hybrid drive units, and other powertrain components are either produced in-house or arrive from specialized manufacturing partners. These components undergo their own precision machining processes. Crankshafts are ground to micron-level smoothness. Cylinder heads are pressure tested for leaks, and valve trains are assembled under cleanroom conditions to prevent particulate contamination. Every engine is hot tested with synthetic oil and run on a bench to simulate driving conditions, ensuring it meets Lexus's strict vibration, noise, and torque standards. In the chassis line, the painted body is now mounted onto its corresponding suspension and drivetrain system. This is performed on synchronized conveyor lines where the body and the chassis meet in a process called marriage. Sophisticated vision systems and robotic arms align the two structures with such precision that no manual corrections are necessary. Once married, the vehicle receives its fuel system, braking components, and exhaust system, each installed by a combination of robots and skilled technicians. Wiring harnesses, which can include several kilometers of cable, are laid out using templates and fixed in place by specialized machines. These harnesses connect the vehicle's electronic control units, sensors, infotainment systems, and safety devices. Interior assembly follows, beginning with the installation of insulation, sound deadening mats, and undercarpet padding. Lexus places a high priority on NVH, noise, vibration, and harshness. So every panel is fitted with dampening materials to ensure a quiet ride. Seats are assembled in a separate clean area and installed using automated arms with torque sensors that ensure fasteners are neither under nor over tightened. Dashboard modules, which include HVAC controls, infotainment screens, and digital displays, are pre-assembled on sidelines and inserted into the cabin in one synchronized motion. The steering column is calibrated for tilt and telescopic movement and connected to electronic steering systems, while airbags and sensors are fitted with strict adherence to safety protocols. Once the interior and exterior trim are installed, including lighting assemblies, mirrors, grills, and body moldings, the vehicle proceeds to the fluid fill area. Here, robotic nozzles inject the precise quantities of engine oil, brake fluid, coolant, transmission fluid, and refrigerant for the air conditioning system. Each fill is tracked by weight and volume sensors to guarantee consistency. After this, the car undergoes wheel mounting and torque checking using specialized tools that record every bolt's torque signature to ensure they meet Lexus's specifications. Now fully assembled, the car enters the dynamic test stage. Every Lexus is driven on a test track or rolling road that simulates real-world driving conditions. During this phase, technicians listen for abnormal noises, feel for vibrations, and monitor electronic systems to confirm everything operates within design parameters. Brake response, suspension feel, steering feedback, and drivetrain behavior are all evaluated in real time. Vehicles equipped with advanced driver assist systems undergo calibration and functional checks using target boards and optical sensors. If any anomaly is detected, the car is flagged and routed to a correction station for adjustments or part replacement. Quality assurance is not a single checkpoint, but a continuous presence throughout the assembly process. Hundreds of sensors, scanners, and cameras monitor every assembly station. Torque tools are networked into the plant's central server to ensure bolts are always fastened correctly. Paint is checked not only by human inspectors, but also by multi-angle robotic sensors that detect flaws invisible to the human eye. Final inspection is carried out by Takumi masters, who evaluate the vehicle's tactile and visual quality. They look at panel gaps, feel the texture of materials, and assess the overall aesthetic with a level of scrutiny that only comes with decades of experience. Once cleared for shipping, the car is fitted with temporary protective coverings on high contact surfaces like the hood, mirrors, and interior trim. It then moves to the logistics center where it's sorted by destination. Lexus uses a just-in-time distribution system to minimize storage time and ensure each vehicle arrives at the dealership in showroom condition. Transport is typically handled via rail or enclosed trucks, depending on the destination. Some markets require additional port processing, such as compliance with regional emission standards or language-specific infotainment updates before the vehicles are delivered to showrooms. What truly sets Lexus apart, however, is not just its meticulous production, but the ethos that underpins it. The Lexus production system, derived from the famed Toyota production system, emphasizes continuous improvement, waste reduction, and human-centered manufacturing. Workers at every level are encouraged to stop the line if they notice an abnormality, a culture known as Jidoka, or built-in quality. Every process is subject to Kaizen, or incremental improvement, meaning the manufacturing floor is in a constant state of optimization. Even the robots are not fixed assets. Their programming is continuously updated based on feedback from human workers. This seamless blend of human mastery and robotic precision results in a vehicle that embodies both technological advancement and handcrafted excellence. From the silent glide of the paint robots to the calm concentration of a Takumi applying finishing touches to a wooden inlay, each Lexus carries within it the philosophy of omotenashi, a spirit of hospitality and attention to detail that transcends machinery. In a world increasingly dominated by automation, the Lexus factory is a compelling reminder that the future of manufacturing lies not in replacing the human touch, but in elevating it. Inside the rugged and powerful world of Jeep manufacturing, toughness isn't just a design principle. It's embedded in every step of the industrial process. Jeep vehicles, renowned for their off-road capabilities and iconic status, are built in factories that combine high-strength materials, advanced robotics, and decades of engineering experience to produce vehicles capable of handling everything from city streets to extreme terrain. The story of how a Jeep comes to life inside a factory is a narrative of precision, durability, and relentless testing, all shaped by a legacy that dates back to World War II. It all began in the early 1940s, when the US military needed a lightweight, go-anywhere reconnaissance vehicle. What followed was the birth of the Willys MB, the direct predecessor to the Jeep. Over the decades, the brand evolved from a military utility vehicle to a global symbol of adventure, strength, and freedom. Today, Jeep models like the Wrangler, Grand Cherokee, and Gladiator are produced in high-tech manufacturing facilities that carry forward the DNA of the original while incorporating the very latest in automotive production technology. The process begins long before the first bolt is tightened. It starts with engineering teams who define the specifications of each new model based on performance expectations, off-road capability requirements, safety standards, and customer feedback. Computer-aided design and simulation tools help model every component, from the ladder frame chassis of a Wrangler to the unibody structure of a Grand Cherokee, ensuring each part is strong, lightweight, and optimized for performance. Crash simulations, airflow analysis, and even water fording simulations are run digitally, months before any physical part is made. Once the vehicle design is finalized, raw material procurement begins. Jeep factories rely heavily on high-strength steel alloys, aluminum, and composite plastics. These materials arrive at the plant as massive coils or billets and are rigorously inspected for imperfections. Each batch is traceable, meaning any material used in a Jeep can be tracked back to its origin. This ensures consistency, compliance with safety regulations, and accountability. These raw materials first enter the stamping plant, where they are transformed into body panels and frame components. Enormous stamping presses, some standing 3 stories tall, shape the steel using dies that apply thousands of tons of pressure. Each panel must conform to strict tolerances, as even a 1mm misalignment could throw off the entire vehicle structure. Jeep vehicles, especially models designed for off-road use, require thicker and more robust structural reinforcements than many consumer vehicles. This means extra ribbing is built into the dies, and additional pass-throughs in the press lines ensure structural rigidity in critical load-bearing areas like wheel arches and suspension mounts. The formed body panels are then routed to the body shop, where robotic welding arms assemble them into the vehicle's skeleton. For a Jeep Wrangler, this means bringing together the floor pan, sidewalls, roof structure, and rear panels into a boxy, trail-ready frame. The welds must be strong and consistent, especially for a vehicle expected to endure torsional flex and harsh impacts off-road. Jeep factories use a mix of MIG welding, laser welding, and resistant spot welding. Over 5,000 welds go into each body, with robots performing the majority, while human technicians focus on quality critical joints, or hard-to-reach spots. A unique aspect of Jeep production, especially for the Wrangler, is the modularity of the body. Doors, roofs, and windshields are designed to be removable, which adds complexity during assembly. Tolerances must be tighter because customers expect parts to detach and reattach easily, without leaks or vibrations. This means extensive calibration and fit testing is built into the body shop workflow. Every door frame and roof panel is test fitted and adjusted using pneumatic tools and laser measuring systems to ensure flawless alignment. Once the skeletal body is complete, it heads to the paint shop, one of the most technologically advanced areas in the plant. The vehicle first undergoes a thorough cleaning and surface preparation. This includes a dip in a phosphate bath to clean off oils and contaminants, followed by electrocoating, where the vehicle is submerged in a tank and an electrical current bonds an anti-corrosion primer to every surface, including hidden cavities. After drying, the vehicle enters the painting booths. Here, robots apply multiple coats of paint, primer, color, and clear in a dust-free environment. Jeep offers bold colors inspired by nature and adventure, such as Sarge Green or Firecracker Red, each mixed with precise pigment ratios and applied with fluidic nozzles that mimic human spray techniques. Each coat is oven-cured to form a resilient finish capable of withstanding UV exposure, mud, salt, and rocks kicked up from the trail. After painting, the body shell enters the general assembly area, the heart of the production line. This is where the Jeep transforms from a metal shell into a fully equipped vehicle. It begins with insulation, sound-deadening materials, and sealants applied inside the cabin. For Jeep models, this includes water-resistant treatments, as many vehicles are designed for water fording. Door seals and body gaskets must meet strict compression and durability standards. Wiring harnesses are installed next, and these are more complex than ever. Modern Jeeps feature hundreds of sensors, infotainment systems, off-road driving modes, and safety technology. These harnesses are laid in place using programmable placement arms and secured with clips, zip ties, and heat shrink tubing, depending on the location and exposure to moisture or vibration. Next comes the marriage of the chassis and powertrain with the painted body. For body-on-frame vehicles like the Wrangler and Gladiator, the heavy-duty steel frame is assembled separately, including solid axles, coil or leaf springs, differentials, skid plates, and suspension arms. The frame is then bolted to the body using hydraulic lifts and torque tools that ensure each fastener meets exact tension values. For unibody models like the Cherokee or Compass, this integration happens earlier in the line with subframes bolted directly to the structure. Jeep powertrains are built for torque, durability, and versatility. Engines such as the Pentastar 5.6, the Hurricane turbocharged inline 4, or diesel options are assembled in parallel engine plants where they undergo machining, balancing, and dyno testing. Each engine is hot tested for leaks, performance, and emissions compliance. Transmissions, whether manual, automatic, or dual clutch, are mated to the engine on a subline, forming the complete drivetrain assembly. This unit is then raised into the chassis using synchronized lifts and installed with precision fasteners that ensure alignment and vibration isolation. Drivetrain components are connected next. Drive shafts, transfer cases, and locking differentials, all essential for Jeep's off-road performance, are installed and calibrated. Specialized torque sensors verify that each fastener is within spec, and camera systems double-check routing and connections. Jeep's 4x4 systems require precise calibration, especially when electronic terrain management systems are used. These allow the driver to switch between mud, sand, snow, and rock crawling modes, adjusting throttle mapping, gear ratios, and traction control accordingly. Now, the vehicle moves into interior and exterior trim assembly. Seats, dashboards, consoles, and trim panels are installed by teams working in pods, with each station responsible for fit, function, and finish. For premium models, like the Grand Cherokee Summit, this includes hand-stitched leather, real wood accents, and digital clusters that must be pixel perfect. Each infotainment screen is tested for dead pixels and software integrity before leaving the station. Rugged models, like the Wrangler Rubicon, get special features such as washable floor mats, reinforced roll bars, and waterproof switches. Exterior components like grills, bumpers, lighting assemblies, and badging are added in tandem, with a final alignment check to ensure symmetry and fit. Next, the vehicle proceeds to the fluid fill station, where all vital systems are charged with fluids: motor oil, transmission fluid, differential gear oil, coolant, brake fluid, power steering fluid, and refrigerant. Each fluid fill is done robotically, with flow meters and digital monitoring to verify quantities and eliminate the risk of leaks. Finally, the Jeep enters a rigorous quality and testing phase. This begins with a rolling road test, where the vehicle is driven on dynamometers to test drivetrain performance, braking, steering, and electronic controls. Special off-road simulations are run to verify that lockers engage, hill descent controls activate, and all-wheel drive functions correctly. Vehicles are then driven over test tracks with potholes, speed bumps, and articulation ramps to simulate real-world terrain. Water intrusion tests involve spraying the vehicle at high pressure from multiple angles to ensure seals hold. Each Jeep undergoes a final inspection by trained quality specialists who look at paint finish, interior trim, panel gaps, and feel for any mechanical irregularities. Light tunnels and tactile checks help identify imperfections. Every vehicle is barcoded and logged, with full traceability of every component and test result. Once approved, the vehicles are sent to the logistics center. Some are loaded onto rail cars for cross-country shipment, while others are driven onto enclosed trucks for dealer delivery. Jeeps destined for export are often protected with shrink wrap, and some may be reconfigured with market-specific hardware or software updates before final delivery. Inside the meticulously engineered world of Corvette production, speed, performance, and precision craftsmanship converge inside one of the most specialized automotive manufacturing facilities in the world, the General Motors Bowling Green Assembly Plant in Kentucky. This is the only place on Earth where every Corvette is built, from the very first weld to the final roar of the engine. From hand-built V8 power plants to aerospace-grade composite panels, the modern Corvette is the result of decades of performance heritage married to cutting-edge manufacturing science. The process of building one of America's most iconic sports cars isn't just an industrial operation. It's an orchestrated symphony of engineering, robotics, skilled labor, and quality control, working together to create a machine that is capable of competing with the best exotic vehicles on the planet. The Corvette's legacy stretches back to 1953, when the very first model rolled off a makeshift production line in Flint, Michigan. It was a lightweight, fiberglass-bodied roadster powered by a modest inline-six engine, but that humble beginning sparked a revolution. Over the decades, the Corvette evolved, gaining V8 engines, refined suspensions, racing pedigree, and global prestige. In 2020, the Corvette took its biggest leap yet. The C8 generation transitioned to a mid-engine layout, fundamentally altering how the car is designed, built, and performs. This change not only shifted the car's balance and handling characteristics, but required a complete rethinking of the manufacturing process. The factory itself was overhauled to accommodate the new architecture, including the installation of hundreds of millions of dollars worth of robotics and tooling, all to support the Corvette's transformation into a true supercar. The process begins with the core of the vehicle, the chassis and structural frame. The C8 Corvette uses a bespoke aluminum space frame that provides high torsional rigidity with relatively low weight. The aluminum arrives at the factory in billet or coil form, sourced from certified suppliers meeting strict metallurgical standards. Before fabrication, each aluminum piece is scanned for flaws using non-destructive testing methods, such as ultrasonic or X-ray analysis. Once cleared, the aluminum is extruded, stamped, or hydroformed into the necessary components, including rocker beams, cross members, and crash structures. The hydroforming process is particularly fascinating. In this technique, aluminum tubes are placed into dies and then expanded into their final shape using pressurized hydraulic fluid. This allows for complex, hollow parts with superior strength-to-weight ratios, ideal for the Corvette's safety and performance needs. After forming, robotic systems with high-precision weld arms begin assembling the frame using a combination of MIG welding, laser welding, and structural adhesives. The fully assembled frame is placed on a rotating jig that allows for 360-degree access, ensuring welds are placed with micron-level precision. Each frame is scanned with a 3D vision system to verify all dimensions before moving to the next station. While the frame is coming together, another crucial part of the Corvette, the body panels, is being fabricated. Unlike most mass-market vehicles, the Corvette's skin is made from lightweight composites, including fiberglass reinforced plastics, carbon fiber, and sheet-molded compounds. These materials provide strength and shape without adding the bulk of traditional steel panels. Fiberglass panels are formed through a process called compression molding, where pre-cut fiberglass mats are placed in heated molds and compressed under extreme pressure with resin. Carbon fiber parts, such as the front splitter or roof panels in high-performance trims, are layered by hand or through automated layup machines, then cured in industrial autoclaves that apply heat and vacuum pressure to harden the epoxy resin binding the fibers. Each panel is hand-inspected for voids, fiber alignment, and surface imperfections before heading to paint. Since composites expand and contract differently than metal, Corvette panels require their own specialized painting process. The painted body panels must not only match each other perfectly, but must maintain color integrity over time, even under high UV exposure and heat. Paint robots apply multiple coats: primer, base, metallic or pearl layer, and clear coat, with each step oven cured. Color matching is so critical that Corvette offers customers a paint inspection under natural light to approve their vehicle's finish before delivery. Back at the main assembly line, the aluminum chassis and painted body panels are now ready to come together. The chassis first moves through the marriage process, where it is combined with the suspension, brakes, steering components, and cooling systems. Each suspension arm is installed using robotic torque tools that log every bolt's torque value in a centralized quality database. Corvette's advanced suspension options, including magnetic ride control and adjustable dampers, are calibrated at this stage using diagnostic computers connected to the vehicle's internal CAN bus system. The next major milestone is the installation of the powertrain. Unlike most vehicles, Corvette engines are not installed en masse by an overhead crane or conveyor. Instead, each engine is mounted into a subframe along with the dual-clutch transaxle and rear differential. Then the entire unit is raised into the car from below using an automated lift platform. This method, called a cradle install, allows for better alignment and reduces stress on the vehicle's structure. The C8 Corvette uses a rear mid-engine layout, so the mounting process is complex and requires exact alignment of multiple mounts, fluid lines, wiring harnesses, and cooling ducts. The engine itself is built at the Performance Build Center, a special clean room inside the Bowling Green factory where trained technicians hand assemble each V8 by hand. In fact, Corvette customers can even pay to participate in this process through the Engine Build Experience program. Every engine is constructed using torque-to-yield fasteners, precision-balanced rotating assemblies, and individually tested components. Pistons are matched by weight within grams. Valve lash is measured and adjusted to strict tolerances. Each finished LT2 or LT6 engine is then tested using a hot run bench that simulates real-world driving conditions. Oil pressure, combustion noise, RPM range, and emissions are all logged before the engine is certified for installation. Once the powertrain is integrated, the Corvette proceeds to the electrical and interior assembly areas. Wiring harnesses are installed first, snaked through the monocoque chassis and connected to control modules. The vehicle's electronic brain includes over 24 modules, managing everything from traction control to wireless connectivity. Technicians perform continuity and resistance tests at every connection point. After electrical setup, the interior components are added, including carbon fiber dash inserts, premium leather seats, and customizable infotainment systems. Materials for the cabin are cut and sewn on-site with real aluminum, suede, and leather used extensively. Each interior is installed by a specialized team that ensures tight fit and finish across every seam, panel, and switch. As the Corvette approaches final assembly, exterior panels are now fitted to the car. Because composite panels are more flexible than metal, special alignment jigs are used to ensure consistent panel gaps and flush mounts. Each door, hood, and hatch is tested for smooth operation. At this stage, every Corvette begins to resemble its final form, with aggressive aerodynamic lines, wide fenders, and the unmistakable mid-engine proportions that define the C8 platform. With the vehicle now complete, it moves into the final inspection and validation zone. Here, a full suite of dynamic tests is run. The Corvette is placed on a 4-post shaker rig to simulate road vibrations and detect any abnormal noises. It is then moved onto a rolling dynamometer where the vehicle is driven up to highway speeds. While engineers test shifting behavior, throttle response, cooling system efficiency, and stability controls. Brake systems are tested for fade resistance and ABS performance. High-speed fans simulate airflow to confirm cooling under load. After dynamic testing, each Corvette is subjected to a water test. High-pressure jets are sprayed from all angles to confirm weather seals and water resistance. A separate light tunnel is used for a full-body visual inspection under high-lux lighting that reveals imperfections in paint, fit, or finish. Each vehicle is signed off by a final inspector who performs a checklist of over 100 items, ranging from alignment and cosmetic perfection to software version checks and VIN registration. If everything passes, the car is moved to the shipping prep area. Protective wrapping is applied to sensitive areas like the nose, mirrors, and roof. Final fluids are topped off, the battery is charged, and tire pressures are adjusted. Corvettes destined for US dealers are loaded onto enclosed trailers, while international units are prepared for shipping in climate-controlled containers. The factory offers a museum delivery program, allowing customers to pick up their vehicle in person at the National Corvette Museum across the street. An experience that includes a factory tour and photo documentation of their car's birth. From molten aluminum to a roaring mid-engine sports car, every Corvette that rolls off the line is a symbol of American engineering at its most passionate and refined. The attention to detail, the fusion of handmade assembly with robotic precision, and the obsessive quality control processes all contribute to a vehicle that isn't just built, it's crafted. For over 70 years, the Corvette has stood as an icon of speed and innovation, and inside the Bowling Green factory, that legacy is forged daily in metal, carbon fiber, and thunder. The story of an H2R does not begin on the assembly line. It begins much earlier, within the metallurgical divisions and materials labs that prepare the raw constituents of the motorcycle's essential components. At this initial stage, the journey starts with a block of high-tensile steel alloy, specifically formulated for the H2R's trellis frame. This isn't ordinary steel. Kawasaki engineers designed the alloy composition to maximize tensile strength while balancing torsional rigidity and ductility. Sheets and tubing are delivered to the fabrication facility in precisely measured cuts, each one traced through an internal lot tracking system for complete traceability. Within the factory, the raw frame tubing undergoes cold drawing, a process that pulls the steel through dies to fine-tune its dimensions and surface integrity. Cold drawing is chosen specifically because it preserves mechanical strength while yielding tight dimensional tolerances, which are critical for the trellis frame's intricate geometric structure. Robotic armatures position each steel tube beneath automated laser cutting heads that slice the tubes into exact segments, using CNC-defined angles to ensure proper later fitment during welding. The accuracy here is staggering. Deviations beyond 0.1 millimeters trigger alerts in the system, halting the production cell for inspection. These cut tubes are then transferred via automated conveyors to a robotic frame welding station. Unlike mass-market motorcycle frames, the H2R's frame is entirely hand-welded, albeit with robotic support for fixturing and alignment. Skilled technicians, each trained for months on frame-specific geometries, perform manual TIG welding to fuse the chromoly steel components together. This welding process isn't just about joining metal. It's a delicate operation, balancing thermal input and cooling rates to avoid internal stress or warping, which could compromise high-speed stability at over 300 kilometers per hour. Once the frame is assembled, it enters a dimensional verification stage utilizing 3D laser scanning. The scanning head, mounted on a 6-axis robotic gantry, creates a digital twin of the physical frame, comparing it to the original CAD model within fractions of a millimeter. If the frame passes all checks, it moves to a powder coating line where it is electrostatically coated and oven cured at controlled temperatures. The specific gloss and hardness of the black frame coating are chosen for both heat resistance and resistance to rock chips and vibration-induced wear. Meanwhile, in another section of the plant, the supercharged engine, the beating heart of the H2R, begins its life in the engine assembly hall. This hall is a restricted environment, temperature and humidity controlled, and acoustically insulated from the rest of the plant. The reason is simple. The inline 4-cylinder engine that powers the H2R is not just another power plant. It's an ultra-high performance 998cc unit, force-fed by a centrifugal supercharger capable of spinning at up to 130,000 RPM. Such precision demands a sterile, meticulously maintained production environment. Engine block castings arrive from Kawasaki's dedicated foundry, having been machined to spec using 5-axis CNC centers. These blocks are inspected using ultrasonic resonance techniques to detect subsurface anomalies that cannot be seen visually or through surface scanning. If the casting passes inspection, it is mounted onto an engine cradle fixture, and the first stage of assembly begins. The installation of crankshaft bearings. Each bearing shell is hand micrometered and color-coded marks are applied to designate their oil clearance class. This step is crucial because the H2R engine tolerances are far tighter than in commuter bikes. The goal is minimal oil film thickness for maximum responsiveness without inducing friction-related failures. After the bearings are installed, the forged steel crankshaft is delicately lowered into the block. This crankshaft, balanced to aerospace-grade tolerances, is laser etched with its unique serial number for tracking and quality assurance. Next, titanium connecting rods and forged pistons are assembled offline on dedicated piston rod mating benches. Each piston is weighed and matched to its rod to within 0.5 grams to ensure uniform reciprocating mass balance. Piston rings are installed using rotary ring expanders that ensure even pressure and no deformation. The piston assemblies are then inserted into the engine block using hydraulic-assisted ring compressors, and the crankshaft is rotated by hand through a flywheel fixture to ensure smooth, unimpeded movement. Even the tiniest resistance would be flagged as an indicator of misalignment or contamination. Once the bottom end is secured and torqued in a cross pattern using digitally calibrated torque wrenches, attention shifts to the cylinder head. The H2R cylinder head is a complex component, machined with pent roof combustion chambers, large titanium valves, and dual overhead camshafts. Valve springs are installed using a pneumatic valve spring compressor, and valve lash is adjusted using precision shims measured to within hundredths of a millimeter. Camshafts, hardened and micro-polished, are mounted on journal caps and rotated to align with timing marks on the crank. The timing chain, a double roller unit, is fed through a guide channel and connected to the crank sprocket, then tensioned using a hydraulic chain tensioner preloaded with assembly oil. Once aligned, the engine is rotated again by hand, and valve timing is confirmed using a laser cam phase analyzer that calculates exact intake and exhaust overlap degrees. Now comes the installation of the supercharger, the defining feature of the H2R. The supercharger is assembled in a separate clean cell. Its impeller, machined from a single billet of aluminum, is balanced using high-speed spin balancers before being mounted to the planetary gear drive. The planetary gear unit, in turn, is gear-driven from the crankshaft and is fitted with helical-cut gears to reduce noise and increase torque handling. Once mated, the entire supercharger is tested in a closed-loop bench system, where it is spun up using a drive motor to simulate load and airflow output. Only if it meets the volumetric efficiency thresholds is it approved for installation onto the engine. As the supercharger is bolted onto the engine using a dedicated torque fixture, the entire power plant assembly is now ready to move to the dyno test cell. But before that happens, it's moved to a pre-test station where all fluids are filled: high-temperature synthetic oil, long-life coolant, and a special break-in fuel blend optimized for seating piston rings under load. The engine is then mounted into a test cradle wired with sensors and bolted to an eddy current dynamometer. Here, engineers run the engine through a programmed break-in cycle, gradually increasing load and RPM while monitoring combustion pressure, knock, oil pressure, and temperatures. Each engine must meet specific power output metrics before it's allowed to leave the test cell. For the H2R, this figure is over 310 horsepower, measured at the crankshaft. Engines falling short are automatically rejected and moved to a forensic diagnostics bench where engineers determine whether the issue lies in fuel delivery, boost pressure, valve timing, or internal mechanical components. Once the dyno-tested engine has passed all performance and durability checks, it is removed from the test cradle and placed onto a specially designed rolling engine dolly. This dolly is more than a simple transport mechanism. It interfaces with hydraulic lift systems, allowing technicians to tilt, raise, and lower the engine precisely for the upcoming frame integration process. Before reaching the frame marriage station, however, the engine is routed through a pre-integration checkpoint where a technician conducts a final surface inspection, verifying all sealing surfaces, torque marks, and component connections. At this stage, all auxiliary components, such as the alternator, starter motor, oil cooler, and coolant hoses, are pre-mounted to reduce complexity during frame insertion. Meanwhile, the painted and fully inspected trellis frame, already cured and cooled from its powder coating process, is mounted on an assembly jig at the chassis preparation station. Here, the steering head bearings are greased and installed using an automated bearing press that ensures equal pressure distribution to avoid warping or damage. Into this steering head, the forged aluminum triple clamps are inserted and torqued to specification using a digital torque wrench with data logging capability. The handlebar mounts are temporarily attached for alignment purposes, but the handlebars themselves will come later in the line. At the engine marriage station, the prepped engine and trellis frame are brought together. A hydraulic lift slowly raises the engine into position beneath the frame, while two alignment pins guide the engine mounting points into perfect register with the frame brackets. 4 titanium bolts, lighter and stronger than traditional steel, are inserted and torqued in a diagonal sequence to avoid any stress concentrations. This step marks the true structural birth of the motorcycle. From this point onward, the machine is no longer a collection of parts. It is a unified mechanical system. With the engine mated to the frame, the motorcycle chassis is now placed onto the primary assembly line, an overhead conveyor system that moves each bike along a guided rail through multiple semi-automated workstations. The first station is the front suspension installation area. The H2R utilizes massive 43mm KYB AOS2 forks, which are fully adjustable and coated with a low-friction DLC layer. Each fork is filled with a precise volume of high-performance suspension oil using a vacuum fill station, then sealed and compressed to check for internal leaks. Once ready, the forks are inserted into the triple clamps and aligned using a digital laser alignment rig to ensure perfectly parallel orientation. Following this, the front wheel assembly, which consists of a Marchesini forged aluminum rim, dual 330mm Brembo discs, and a Pirelli Slick racing tyre, is rolled up to the workstation. The wheel is mounted onto the axle, and the Brembo M50 monoblock calipers are installed with anti-vibration shims. The brake lines are routed along the fork legs using pre-formed clips, and each banjo bolt is torqued and marked with a color-coded paint pen for visual confirmation of completed steps. Parallel to the front suspension assembly, another robotic cell is preparing the swing arm sub-assembly. The H2R's single-sided swing arm is a hollow, forged aluminum unit with internal stiffeners. It is laser welded and then machined to accept the axle carrier and chain adjusters. Once verified for alignment using a 3D measurement gantry, the swing arm is connected to the frame using a solid pivot bolt, then connected to the rear shock. The rear suspension is a gas-charged KYB monoshock unit, also fully adjustable, and mounted on a rising rate linkage system for progressive damping under heavy loads. With front and rear suspension in place, the H2R is now a rolling chassis capable of supporting its own weight. At this point, the conveyor system gently lowers the motorcycle onto a rolling dolly with locking casters, freeing up the overhead rail for the next unit. The rolling chassis is pushed manually to the next station, the electronics and wiring harness integration bay. Unlike lower-tier motorcycles, where wiring is often installed as a single unified harness bundle, the H2R employs a modular wiring system. Multiple sub-harnesses for the engine control unit, traction control system, data logger, ABS system, and dashboard are installed independently, with each module having its own waterproof snap lock connector. The main harness is routed through the spine of the frame, secured with P-clips and thermal-resistant sleeves to protect from engine heat. Each connector is scanned using an RFID tool to ensure proper mating, and the system performs a low-voltage continuity check before proceeding. Once the electrical systems are routed, the control units are mounted in their designated locations. The inertial measurement unit is mounted beneath the seat. The ECU is housed in a vibration-isolated tray behind the headstock, and the quick-shifter sensor is attached to the gear linkage rod. The dashboard, a full-color TFT display, is installed into the carbon fiber front cowl support and wired into the CAN bus network. With control systems in place, the next stage is the installation of the fuel system. The H2R's fuel tank is not merely a container, it is a shaped aluminum shell with internal baffles and foam inserts designed to reduce sloshing during extreme cornering. Each tank is pressure tested at 1.5 times normal operating pressure to check for leaks. A high-flow fuel pump is mounted internally, and the tank is lined with a corrosion-resistant coating that protects against ethanol degradation. The tank is installed onto rubber isolators on the frame spine and connected to the fuel rail via quick disconnect couplings. Underneath the fuel tank, the intake system comes together. The airbox is a sealed high-capacity plenum chamber designed to handle pressurized air from the supercharger. It features a ram air intake duct and a high-flow air filter made from synthetic fibers. Sensors for intake air temperature and pressure are inserted, and the throttle bodies, ride-by-wire, electronically controlled units, are bolted directly to the intake ports. The supercharger outlet feeds directly into the airbox, and a blow-off valve is installed to regulate excess pressure during throttle closure. Once all intake and fuel connections are secured, the exhaust system is installed. The H2R utilizes a titanium exhaust header that is hand-welded and purge-welded from multiple conical sections. Each pipe is flow bench tested prior to assembly to ensure even back pressure across all 4 cylinders. The exhaust system includes a collector and a short, undertail silencer, designed to reduce weight and maintain optimal power output with minimal restriction. Sensors for oxygen content and exhaust temperature are threaded into the headers and linked to the ECU. At this point, the bike is fully assembled mechanically, but bodywork has not yet been applied. That comes in the next segment of the production process. But before that, the motorcycle moves into the first startup and diagnostic bay. Here, technicians connect a master diagnostic tablet to the ECU via the OBD port. The system runs a full checklist, verifying sensor functionality, fuel pump pressure, throttle actuator operation, and system voltages. Once verified, the bike is started for the very first time. This initial start is a tense and critical moment. The technician listens closely for any abnormal mechanical noise, monitors the idle speed, checks for warning lights on the TFT display, and ensures that oil pressure rises immediately upon startup. The engine is allowed to idle until it reaches operating temperature, during which time the cooling fan, radiator circulation, and combustion balance are all evaluated. Any deviation from spec prompts an immediate stop and transfer to the diagnostic cell for further investigation. If the startup test is successful, the motorcycle is shut down and moved to the fluid leak test station. Here, a UV dye is added to the oil and coolant systems, and the bike is placed under black light to reveal any possible leaks at hoses, joints, or gaskets. Pressure is applied to the cooling system using a sealed radiator cap rig, and the oil system is pressurized via a pneumatic pump. This ensures that even micro leaks are detected before the bike proceeds to final cosmetic assembly. With all functional systems now tested and verified, the powertrain mounted, the electronics integrated, and the fluids checked for sealing integrity, the Kawasaki Ninja H2R is finally ready to receive what many consider its most striking feature, its full carbon fiber bodywork. Unlike plastic fairings found on standard motorcycles, the H2R's aerodynamic surfaces are crafted entirely from pre-preg carbon fiber panels that are formed, trimmed, and finished in a tightly controlled composites facility within Kawasaki's aerospace division. Each carbon panel, from the sculpted front cowl to the aggressive side fairings to the single-piece tail section, begins life as a sheet of carbon fiber impregnated with epoxy resin. These sheets are hand-laid into CNC machined aluminum molds, layer by layer, with careful attention to fiber orientation and overlap. This layup process determines the final strength and stiffness of the component. And technicians follow a digital blueprint showing precisely where each ply must be placed. Once the layup is complete, the mold is vacuum sealed inside a heat-resistant bag and placed into an autoclave. In the autoclave, the part is subjected to high temperature and pressure, curing the resin and fusing the carbon plies into a single monolithic shell. The process takes several hours, during which the exact pressure and thermal cycle are carefully controlled and logged. After curing, the mold is cooled and the part is demolded and sent to the trimming station. Here, 5-axis CNC water jet cutters remove excess material and create mounting holes, while laser measuring arms verify dimensional accuracy down to fractions of a millimeter. Once trimmed, each body panel goes through a polishing and surface inspection process. Technicians in cleanroom suits buff the surface to prepare it for paint, but for the H2R, this isn't just a cosmetic paint job. It's a defining visual signature. The entire carbon shell is sprayed with Kawasaki's proprietary mirror finish paint, a multi-layered formula that gives the H2R its iconic black chrome look. This paint contains a layer of silver-infused base coat that reflects light like a mirror, followed by multiple layers of clear coat that are wet sanded and polished between applications. The painted carbon fiber parts are then cured in low dust ovens at carefully controlled temperatures. When they emerge, they undergo final inspection under polarized lighting to reveal any imperfections invisible to the naked eye. Only when each piece passes this inspection are they released to the final cosmetic assembly line. Back in the main assembly hall, the rolling chassis is now stationed at the fairing installation bay. Here, a team of 2 technicians works on each unit, using soft-gloved hands and non-marring tools to install the carbon fiber bodywork. The upper cowl is mounted first, secured to a lightweight subframe using vibration-resistant fasteners. The side fairings follow next, installed with grommeted bolts and lined with thermal insulation on the inner surfaces to protect against engine heat. The winglets, a defining aerodynamic element of the H2R, are bolted to the sides of the front fairing using precision jigs. These carbon fiber strakes generate downforce at high speeds and are carefully aligned to match the factory's computational fluid dynamics models. The tail section, which includes the seat pan and integrated rear lights, is installed last. It slots over the subframe like a precision machined cover, secured with hidden fasteners that leave the outer surface clean and uninterrupted. The final visual pieces include the windscreen, made of high-impact acrylic formed over a heated vacuum mold, and the mirrors, which are unique to the H2R in that they are replaced by aerodynamic blades due to its track-only designation. These aerodynamic devices further contribute to the overall downforce and high-speed stability of the motorcycle. With all external components now in place, the motorcycle advances to the lighting and display verification stage. Even though the H2R is not street legal and lacks conventional headlamps, it still features essential lighting systems for track use, including brake lights and dashboard illumination. A diagnostic terminal is connected once more to the onboard electronics, which triggers all LEDs, signal displays, and digital readouts. Any pixel dropout or timing issue in the TFT display is immediately flagged, and the dashboard is swapped out before the motorcycle proceeds. The next phase is torque auditing. Using a handheld digital wrench interface, a technician rechecks every critical fastener on the motorcycle, referencing a torque database specific to the H2R. Each bolt, from the engine mounts to the suspension linkages to the brake calipers, is checked, and the data is wirelessly transmitted to a central quality control server. This system creates a complete torque audit trail for every unit, ensuring that no component is under or over-tightened, which could lead to safety issues under track loads. Following torque audit, the motorcycle is moved to the final mechanical verification bay, a rolling road dynamometer enclosed in a safety chamber. Unlike the earlier engine dyno test, this test evaluates the entire drivetrain system, including wheel alignment, chain tension, gearbox operation, and traction control responsiveness. The motorcycle is strapped down securely onto a rotating drum, and a technician rides the bike through a simulated series of track laps using paddle inputs to shift gears, apply throttle, and trigger braking. The onboard IMU and traction control system are monitored in real time to assess how the electronic aids respond under aggressive load transitions. One particularly crucial part of this test is the quickshifter evaluation. The H2R uses a bidirectional quickshifter that allows for clutchless upshifts and downshifts under load. The dyno software simulates various throttle and RPM combinations while the technician triggers shifts. Sensors measure delay time between shift input and gear engagement, and the ECU adjusts the ignition and fuel cut profile dynamically. If lag or false neutrals are detected, the quickshifter sensor or shift drum is re-inspected. Following dyno verification, the motorcycle is shut down and allowed to cool under controlled airflow. It is then cleaned using ionized air to remove any dust or debris collected during testing and rolled into the inspection corridor, a quiet, well-lit area reserved for aesthetic and dimensional verification. Here, trained inspectors examine every square centimeter of the motorcycle's surfaces under fixed-angle lighting rigs that highlight reflections and contours. They check for paint consistency, panel fitment, fastener flushness, and emblem placement. The final inspection is concluded with a checklist signed by a master inspector who holds clearance to certify H2R units for packaging. A QR-coded certification tag is applied beneath the seat, containing digital records of every test, torque, spec, and visual check the motorcycle has passed. This tag remains with the bike for life, accessible by service centers and authorized Kawasaki technicians. At this point, the motorcycle is ready for crating and shipping, but before that occurs, a factory photographer captures high-resolution images of each unit for archival and legal purposes. These photos document the visual condition at the time of shipment and are stored alongside each VIN's production history. The H2R is then rolled into the final staging area, a climate-controlled packaging room where each motorcycle is carefully enclosed in a custom-built steel and wood crate. The front wheel is braced, the suspension compressed slightly with straps, and the bike is cocooned in protective foam. Every surface prone to scratching is wrapped with a low-tack film. Accompanying the motorcycle is a documentation pack that includes a certificate of authenticity, a technical user manual, a tuning guide, and the special tools required for trackside maintenance. Now ready for departure, the crated H2R is scanned into the logistics database and scheduled for dispatch. Its destination could be a private collector's garage, a professional racing team's paddock, or a high-end performance dealer specializing in exotic motorcycles. Once the Kawasaki Ninja H2R has been crated and logged into the factory's outbound inventory system, its journey through the global supply chain begins. The finished motorcycle, now nestled inside a reinforced steel-tubed crate with engineered shock absorption inserts and padded contact points, is not treated like standard inventory. This is not mass-market production. Each unit is registered and scheduled for delivery with the same level of care typically reserved for aerospace-grade cargo or high-value prototype machinery. The H2R crate is fitted with a tamper-evident seal and a GPS-enabled tracking unit. This small battery-powered device is embedded in the crate frame and continuously broadcasts location, temperature, and shock readings throughout the duration of the shipment. The goal is absolute transparency and control. Kawasaki's logistics division uses a centralized tracking portal to monitor every H2R in transit, ensuring that any anomaly, a sudden temperature spike, an excessive tilt angle during forklift handling, or an unexpected deviation from a scheduled route triggers a real-time alert and investigation. Within the Kawasaki factory's outbound logistics terminal, all outgoing H2Rs are staged in a secure area awaiting carrier pickup. This area is isolated from regular shipping docks and utilizes biometric access controls. When transport is scheduled, only certified freight handlers are permitted to load the crated bikes onto specialized trucks equipped with air ride suspension systems. These vehicles reduce vibration and road shock that could otherwise stress the precision-fitted carbon components or delicate electronics inside the crate. Each transport vehicle is assigned a specific destination hub, most commonly one of Kawasaki's global distribution centers. These hubs, located strategically in Europe, North America, the Middle East, and Asia, are more than just warehouses. They are hybrid facilities combining bonded customs zones, climate-controlled storage, and dealer preparation stations, all operating under strict quality assurance protocols. When a truckload of H2R units arrives at one of these hubs, the unloading process is supervised by Kawasaki regional logistics managers. Each crate is inspected for seal integrity and then scanned into the regional inventory management system using the embedded RFID and QR codes. For units destined for overseas markets, international freight forwarding is used. Crates are loaded into secure ISO shipping containers fitted with humidity control packs and shock-damping floor mounts. These containers are then booked onto cargo ships under insured, high-priority manifests. During ocean transit, the environmental monitoring systems embedded in the H2R crates continue logging data, which is uploaded via satellite uplink every 12 hours. When the containers reach port, customs clearance is expedited through Kawasaki's import-export licensing system, which pre-registers each motorcycle's VIN with the appropriate government authorities to simplify the paperwork associated with limited use non-street legal vehicles. Once the motorcycles arrive at their respective dealer prep centers, they are again moved using air ride trucks and secured holding bays. The dealer-level uncrating process is perhaps one of the most sensitive moments in the entire chain. These centers are equipped with padded flooring, overhead cranes, and specialized unboxing stations designed specifically for ultra-high performance motorcycles. Each crate is disassembled manually, using torque-limited tools to avoid overstressing any fastener. The protective wrap and foam buffers are removed, and a technician conducts a full visual inspection before any mechanical interaction occurs. At this point, the motorcycle is still in a semi-dormant state. While fully assembled at the factory, the H2R is shipped with several systems disabled or set to low activation mode. For example, the ECU is placed in a transport-safe state to prevent any unauthorized ignition or tampering during transit. The traction control system and launch control features are also disabled until activation codes are entered through the factory diagnostic tablet. These codes are provided only to certified Kawasaki race dealer technicians who have completed a specialized training program exclusive to the H2R platform. The first step during dealer prep is to activate the motorcycle's electrical systems. A lithium-ion high-output battery, which was shipped separately to avoid power drain or risk of damage, is installed using a torque-calibrated battery tray mount. The diagnostic tablet is then connected, and the technician runs a software handshake that reactivates the ECU, initiates a full sensor sweep, and calibrates the electronic throttle bodies to their neutral closed position. This is followed by a firmware update if required, ensuring that the bike is running the latest version of Kawasaki's proprietary control logic, an intricate blend of traction, wheelie, slide, and launch control algorithms designed for elite track use. Fuel is then added to the tank, typically a high-octane, ethanol-free race blend sourced by the dealer. This ensures consistent combustion characteristics for the first startup under the dealer's supervision. The cooling system is topped off with pre-mixed long-life coolant, and brake fluid levels are checked. While all systems were previously pressure tested at the factory, this step ensures that nothing has been compromised during transport. The first dealer-level ignition is performed under controlled conditions. The motorcycle is mounted on a paddock stand with wheel chocks and exhaust ventilation systems in place. The technician initiates the ignition cycle, monitors the startup process, and allows the bike to idle while all systems reach operating temperature. During this time, the technician observes engine temperature, oil pressure, throttle responsiveness, and warning indicators. Once warmed up, the throttle is blipped to ensure proper response from the supercharger system. A high-pitched whine confirms that the planetary gear-driven supercharger is spinning freely, and boost sensors are checked to verify pressure increase under transient throttle input. Next comes dynamic system calibration. The dealer technician enters a closed test loop menu via the diagnostic interface, and the motorcycle performs a series of controlled internal tests. These include throttle plate synchronization, IMU pitch and roll calibration, wheel speed sensor checks, and brake pressure modulation trials. These diagnostic steps ensure that all ride assist systems are correctly aligned and functioning before the motorcycle is released to the client. Before final delivery, cosmetic detailing is performed. The bike is cleaned using non-reactive anti-static cloths and waterless detailing sprays to preserve the mirror finish. Tire pressure is adjusted to the recommended range for track delivery, and chain slack is fine-tuned based on the factory's specification under rider weight simulation. The data logging module, if the customer has opted for the full telemetry package, is also installed at this stage, including its GPS antenna and onboard SD card reader. At this point, the motorcycle is ready for customer delivery, but the H2R is not simply rolled out onto the sales floor. In most cases, the delivery is either performed at a private unveiling event or within a dedicated performance showroom, often involving customer briefings, technical walkarounds, and personalized instruction. The purchaser receives a digital service log, a registration keycard for the diagnostic system, and, depending on region, a certificate of ownership detailing the motorcycle's serial number and place of manufacture. Some customers even receive a titanium plaque etched with their VIN, engraved at the factory using the same fiber optic laser that marks engine components. For customers intending to race the bike, additional services are offered. These include initial track setup, suspension tuning based on rider weight and intended circuit, and ECU mapping optimization. Kawasaki certified race engineers are sometimes deployed directly to high-profile clients to help integrate the bike into a team's racing fleet or private collection. In total, from the moment an H2R begins its life in the alloy preparation bay to the moment it is fired up in a client's garage or paddock, the process spans multiple continents, dozens of specialists, and a series of rigorously enforced quality checkpoints. No step is accidental. Every decision, from the type of crate to the orientation of the brake lines during shipping, is designed to protect and preserve the uncompromising nature of the Ninja H2R.